Subscribe to the channel and like the video. Somewhere, deep in the star-studded fabric of our Milky Way, there is a celestial elder whose very existence once threw science into a state of puzzlement. Imagine a star so ancient that its age seemed to defy the very clockwork of the cosmos. A star that, according to early calculations, was older than the universe itself. The idea sounds like science fiction, the kind of plot twist you'd expect in an interstellar mystery novel. Yet, for decades, astronomers looked at one particular stellar relic, known as the Methuselah Star, and asked the same bewildering question: how could something inside the universe be older than the universe itself? This was not a case of poetic exaggeration or cosmic folklore. It was a real, mathematical problem. The universe, as determined by modern cosmology, is about 13.8 billion years old, a figure established by studying the cosmic microwave background, the afterglow of the Big Bang. And yet, early measurements of the Methuselah Star suggested it might be around 16 billion years old. That's more than 2 billion years older than the universe. If you pause to think about that, it's not just odd, it's logically impossible. You can't have a child who is older than their parent, and you can't have a star older than the universe that gave birth to it. The controversy sparked debates in astrophysics. Was there something fundamentally wrong with our understanding of stellar evolution? Could our cosmic age estimate be off? Or was the problem hidden in the way we measured the star's properties? Its brightness, distance, and chemical composition? This was more than just an astronomical curiosity. It was a potential crack in the foundation of cosmology. If the star's age truly exceeded that of the universe, it could mean that our Big Bang timeline was incomplete. Or, in the most radical interpretations, that the universe didn't begin the way we thought it did. The Methuselah Star's apparent defiance of time drew attention because of how starkly it clashed with one of the most well-established numbers in science: the universe's age. That 13.8 billion year figure isn't a casual guess, it's supported by multiple lines of evidence. The expansion rate of the cosmos measured by Hubble's law, the distribution of galaxies, and the precise temperature variations in the cosmic microwave background radiation. So, if this star truly exceeded that age, either the star's data was wrong, or something monumental was missing from our picture of reality. The scientific community didn't jump to rewrite the history of the universe right away. Instead, they dug deeper, refining observations, rethinking the assumptions behind the methods, and bringing in more powerful tools to resolve the mystery. Over time, what emerged wasn't just a corrected estimate, it was a deeper appreciation of how subtle and interconnected the universe's story really is. The Methuselah Star became a symbol of how science works: bold claims, careful investigation, and an ever-evolving understanding of our cosmic home. In other words, the phrase "a star older than the universe" wasn't just a headline-grabbing oddity. It was an open invitation to explore the boundaries of what we know, and more importantly, to challenge what we think we know. The Methuselah Star, formerly designated HD 140283, is one of the most studied and celebrated objects in the night sky. Not because it's bright, colorful, or visually spectacular, but because it's an unassuming, ancient treasure. If you looked up at it without knowing its story, you'd see nothing remarkable. It's a faint, yellowish star that can only be spotted with the help of a telescope or binoculars under good conditions. But hidden behind its modest appearance is an extraordinary history, one that reaches back almost to the birth of the universe itself. HD 140283 resides in the constellation Libra, which is best known for forming part of the zodiac. The star's location isn't in the bustling spiral arms of the Milky Way where young, hot, blue stars thrive. Instead, it belongs to what astronomers call the galactic halo, a roughly spherical region surrounding the Milky Way's main disk. The halo is home to ancient, metal-poor stars and globular clusters that formed in the galaxy's earliest days. Stars here are often wanderers on long, looping orbits that take them far above and below the galactic plane, sometimes plunging through the Milky Way's disk before swinging back out into the vast halo again. HD 140283 is one such traveler, with a motion that suggests it didn't even originate in the Milky Way's central disk. In fact, its trajectory hints that it may have been born in a small dwarf galaxy that was later absorbed by our own during the chaotic mergers of the early universe. From Earth's point of view, HD 140283 lies about 190 light-years away, practically a next-door neighbor in galactic terms. This is close enough for astronomers to study it in exquisite detail. Many of the oldest stars are much farther away, making them faint and hard to measure with precision. The Methuselah Star's proximity is part of what makes it such an invaluable subject for research. We can observe it without the interference of heavy interstellar dust clouds or the distortions that plague measurements of more distant objects. In terms of stellar classification, HD 140283 is a population 2 subgiant star. Let's unpack what that means. The term population 2 refers to an older generation of stars formed early in the history of the universe, before the cosmos had been significantly enriched with heavy elements created by earlier stellar generations. These stars have low metallicity, meaning they contain far fewer elements heavier than helium compared to younger, population 1 stars like our Sun. The subgiant part of its classification means that HD 140283 has exhausted the hydrogen fuel in its core and has started the slow transition away from the main sequence, on its way toward becoming a red giant. In other words, it's in a middle-aged phase of stellar evolution, but in this case middle-aged is misleading. This star has been around since the dawn of time, so its middle age is still staggeringly old. The star's motion across the sky also reveals something extraordinary. HD 140283 is moving rapidly relative to our Sun, so fast that it's one of the fastest moving stars visible from Earth. Its speed and direction suggest that it doesn't share the same rotational motion as the Milky Way's disk. Instead, it plunges through our galaxy on a tilted, elongated path, another clue pointing to its halo origins and possible extragalactic birth. It's worth noting that the Methuselah Star's apparent brightness is faint compared to the Sun, even though it is intrinsically about twice as luminous. This is because it's much farther away than the Sun, and also because it's slightly cooler, giving it a yellowish hue rather than the intense white blue of hotter, younger stars. Its spectrum, light broken down into its component colors, provides a treasure trove of information about its chemical composition, temperature, and motion. It's through this spectral analysis that astronomers first recognized just how little metal content the star had, which in turn led them to suspect it was an ancient relic. HD 140283's uniqueness lies not in its size, mass, or brightness, but in its cosmic age and chemical purity. If stars were like trees, with annual growth rings revealing their age, HD 140283's rings would stretch back nearly to the first cosmic dawn. Its chemical makeup suggests it formed at a time when the universe had only recently cooled enough for the first stars and galaxies to begin shining. Back then, the cosmos was a very different place, mostly hydrogen and helium, with only trace amounts of heavier elements produced by the first generation of stars, known as population 3 stars. The location of HD 140283 within the halo also puts it in a relatively uncrowded stellar neighborhood. There are no massive, luminous stars nearby pouring out radiation that could interfere with observations. This quiet location, coupled with its closeness to Earth, made it an ideal target for the Hubble Space Telescope and other observatories trying to unravel the mystery of its age. From the ground, even large telescopes can measure its position and brightness, but space-based observations allow astronomers to track its position against the background of much more distant stars with unmatched precision. Interestingly, the Methuselah Star has been catalogued and studied for over a century. Its formal designation, HD 140283, comes from the Henry Draper Catalogue, a monumental early 20th century effort to classify stars by their spectral type. For decades, it was simply one of many high-velocity halo stars noted for its peculiar motion and low metallicity. It wasn't until more precise measurements of its luminosity and distance were made that its extreme age became apparent, and that's when it earned its biblical nickname. The galactic coordinates of HD 140283, what you'd use if you were plotting it in a 3D map of the Milky Way, place it in a position that suggests it's just passing through our region of space on a long orbital journey. Its past path likely carried it thousands of light years away from the Sun, and in the distant future, it will drift off again, leaving astronomers in some future epoch to wonder about the fleeting presence of this ancient wanderer. If you could stand on a hypothetical planet orbiting HD 140283, a purely speculative idea, as such an old star likely wouldn't host the kind of planetary systems we're used to, it would be like living next to a cosmic museum piece. Every photon of light from the star would be a whisper from the early universe, a steady reminder that your sun had been shining since before the Milky Way was fully formed. In summary, the Methuselah Star is a population 2 subgiant star with extremely low metallicity. Located about 190 light-years from Earth in the constellation Libra. a remember of the galactic halo, likely captured from a smaller galaxy long ago. A rapidly moving relative to the Sun, on a tilted orbit through the Milky Way. A remarkably well-positioned for study due to its proximity and minimal interference from dust and nearby stars. Its location and properties make it one of the most important time capsules in astronomy. A star that lets us peer back into the earliest chapters of cosmic history without having to leave our own celestial backyard. The nickname Methuselah is more than just a catchy label. It's a symbolic bridge between ancient human storytelling and the unimaginably long timescales of the cosmos. In the Hebrew Bible, Methuselah is a figure from the book of Genesis, renowned as the longest-lived human in Scripture. According to the text, he lived for 969 years, an almost mythical span even by biblical standards. Over time, Methuselah's name has become a cultural shorthand for extreme age, whether you're talking about a tree, a wine, or, in this case, a star. When astronomers first realized that HD 140283 might be far older than any other star they had studied, and possibly older than the universe itself, it didn't take long for the nickname to emerge. This wasn't an official designation like HD 140283 or a scientific classification. It was more of an affectionate moniker, a way for scientists, journalists, and the public to immediately grasp the heart of its mystery. Calling it Methuselah instantly conjured the image of a cosmic elder, a survivor. From the dawn of time still burning quietly in our corner of the galaxy. In a way, the nickname does double duty. On the one hand, it emphasizes the sheer, awe-inspiring antiquity of the star, its lifespan stretching back to epochs when the universe was in its infancy. On the other, it humanizes the star. Saying HD 140283 might make it sound like a serial number on a lab specimen, but Methuselah feels more like a title bestowed on an elder of great respect. This human touch has helped make the star a popular topic not just in astronomy circles, but in science outreach, documentaries, and educational videos. The biblical Methuselah himself is often remembered as a symbol of endurance. He lived through the generations leading up to the great flood of Noah's time, spanning nearly a millennium of history in the narrative. The parallel with the star is striking. HD 140283 has lived through a vast sweep of cosmic events, from the turbulent period after the Big Bang to the formation of galaxies, the birth and death of countless other stars, and even the rise of planetary systems like our own. If Methuselah the man was seen as a living link to a nearly mythical past, then Methuselah the star is an actual, physical link to the very first chapters of the universe. There's also a poetic irony in the comparison. Methuselah's 969 years may sound impossibly long in human terms, but in stellar terms it's not even the blink of an eye. Stars like HD 140283 measure their lifespans not in centuries or millennia, but in billions of years. The number astronomers once estimated for Methuselah Star's age, 16 billion years, is so far beyond our everyday sense of time that it almost requires metaphor to make it relatable. By reaching for a name steeped in ancient storytelling, scientists gave people a handle on the ungraspable scale of stellar time. It's important to remember that the choice of name doesn't change the science. It's still an F-type subgiant star with a specific luminosity, metallicity, and trajectory. But in the public imagination, Methuselah Star makes it easier to see the object as more than just data points. It becomes a character in the unfolding drama of cosmic history. You might imagine it as a wise, weathered traveler that has seen the galaxy change countless times, carrying secrets in its core from an era when the universe was still young and raw. Other ancient entities in nature have earned similar nicknames. There's the Methuselah tree in California, a bristlecone pine more than 4,800 years old. There are ancient strains of bacteria nicknamed after Methuselah for surviving in extreme conditions for geological timescales. These names function like small myths in our modern age, connecting the deepest past to the present in a way that raw numbers often cannot. HD 140283 fits perfectly into this tradition. And here's the subtle beauty of the name: it sparks curiosity. People hear Methuselah Star and wonder immediately, why is it called that? What makes it so old? How do we even know a star's age? The name becomes an invitation to dive into the science, to move from legend to data, from metaphor to measurement. It draws people in, and once they're curious, they can follow the thread into the complex but fascinating details of stellar evolution, galactic archaeology, and cosmology itself. So while Methuselah may have its roots in an ancient text, The star that bears its name has a far older story, one written not in human language, but in the nuclear furnaces of the early cosmos. The biblical Methuselah might have been remarkable for living through 1,000 years of human history, but HD 140283 has been burning for nearly the entire history of time itself, a living relic that predates our Sun, our planet, and even the spiral arms of the Milky Way. When astronomers say the Methuselah Star is about 190 light-years away, it's easy for that to sound like a vague, really far measurement. After all, most of us think in miles or kilometers, maybe thousands for a long road trip, or tens of thousands when talking about circumnavigating Earth. Light years? That's a completely different order of magnitude, numbers so large they can feel abstract. But in cosmic terms, 190 light-years is astonishingly close. To understand why, we have to remember what a light-year actually means. It's the distance light travels in a vacuum over the course of 1 year. Light zips along at nearly 299,792 kilometers per second, about 186,282 miles per second, which means in just 1 second it could loop around Earth more than 7 times. In a year, it covers about 9.46 trillion kilometers, or roughly 5.88 trillion miles. Multiply that by 190, and you get a distance so vast it's hard to visualize, about 1.8 quintillion kilometers. And yet, that staggering number is practically just down the street in our galactic neighborhood. The Milky Way is about 100,000 light-years across. That means the Methuselah Star is less than 0.2% of the way across our galaxy from us. If the Milky Way were scaled down to the size of North America, Methuselah would be like a neighbor living a few blocks away. This closeness is one of the reasons HD 140283 has become such an important subject of study. Many other extremely old stars, especially those with low metallicity, are found in the outer halo of the galaxy or in distant globular clusters, often tens of thousands of light-years away. Observing them requires peering through thick clouds of interstellar dust, which can distort their light and complicate measurements. Methuselah, on the other hand, sits close enough that we can observe it with relative clarity, free from many of those obstructions. Its proximity also makes it possible to measure its parallax, the apparent shift in position of the star against the background of more distant stars as Earth orbits the Sun, with exceptional precision. This is a crucial step in determining its exact distance, and in turn, its intrinsic brightness, or luminosity. Without an accurate distance, astronomers can't reliably calculate its age, because the star's luminosity is one of the key inputs for stellar age models. In fact, when the Hubble Space Telescope measured Methuselah's parallax more precisely, it significantly improved our understanding of the star's true age, helping to bring it in line with the age of the universe. To put the Methuselah Star's 190 light-year distance in perspective, the Sun's nearest stellar neighbor, Proxima Centauri, is about 4.24 light-years away. The brightest star in the night sky, Sirius, is about 8.6 light-years away. The center of the Milky Way is roughly 26,000 light-years away. So, Methuselah is about 45 times farther than Sirius, but still unimaginably closer than the majority of stars astronomers study in deep sky surveys. If you could somehow hitch a ride on the fastest spacecraft humanity has ever built, NASA's Parker Solar Probe, which reaches speeds of about 700,000 kilometers per hour, 430,000 miles per hour, it would still take you over 3,000 years to get there. That's a mind-bending reminder of how vast space is, even within our so-called backyard. Its proximity has another interesting side effect. Despite being incredibly old, Methuselah is faintly visible through amateur telescopes. You wouldn't notice anything remarkable by looking at it, just a modest, yellow-white point of light, but the knowledge of what you're seeing transforms the experience. Every photon entering your telescope from that star began its journey 190 years ago, before the invention of the telephone, before Darwin published On the Origin of Species, before the American Civil War. By the time that light arrives in your eye, the star has already moved slightly in its orbit, the Earth has rotated tens of thousands of times, and history has marched on. Yet here it is, a messenger from a near neighbor that has survived since the dawn of time. It's rare for a star of such antiquity to be found so close. Most halo stars are far away, and most nearby stars are relatively young. Methuselah's closeness is a happy accident for science. It's as if an archaeological artifact from the very first human civilizations had somehow ended up in your own backyard, ready for inspection with the most advanced tools available. That accessibility has allowed astronomers to revisit and refine their observations repeatedly, improving their models and narrowing the uncertainties in its age estimate. So while 190 light-years is unfathomably far on human scales, in galactic terms, Methuselah is right next door, a conveniently placed relic from the earliest days of the cosmos, sitting close enough for us to measure with remarkable accuracy. The story of the Methuselah Star truly caught the world's attention because of a single, jaw-dropping result. Early measurements indicated it was 16 billion years old, a number that, if true, would throw the very foundations of cosmology into question. At first glance, 16 billion versus 13.8 billion years might not sound like an enormous gap, especially when dealing with cosmic timescales. But the difference is colossal when you remember what these numbers represent. The age of the universe, 13.8 billion years, is one of the most precisely determined figures in all of astronomy. It comes from multiple, independent lines of evidence, most notably the data from the Cosmic Microwave Background, CMB, gathered by missions like WMAP, Wilkinson Microwave Anisotropy Probe, and Planck. These spacecraft measured the faint afterglow of the Big Bang with extraordinary precision, allowing scientists to calculate not just the age of the universe, but its rate of expansion, matter composition, and other key properties. The age of the universe isn't just an arbitrary statistic. It's the upper limit for the age of anything that exists within it. You can't have planets, galaxies, or stars that are older than the cosmos itself. The very first stars didn't appear instantly after the Big Bang. They formed only after the universe cooled enough for hydrogen atoms to come together, roughly 100 to 200 million years after the event. That means the oldest stars should top out at just under 13.8 billion years in age, give or take some uncertainty. So when HD 140,283's early age estimates clocked in at 16 billion years, it was more than just a quirky outlier, it was an apparent impossibility. The analogy often used is that it's like finding a birth certificate for a person who supposedly lived before their parents were born. Either the birth certificate is wrong, or our entire understanding of the family tree is flawed. In the early 2000s, researchers using data from ground-based observatories and the Hubble Space Telescope derived this startling 16 billion year figure based on the star's luminosity, temperature, and chemical composition. These measurements fed into stellar evolution models that simulate how stars change over time. In these models, older stars have certain predictable characteristics. They are generally cooler, have lower metallicity, and, depending on their mass, can evolve off the main sequence into subgiant or red giant phases. The Methuselah Star's parameters put it in a category that, at the time, matched only an extremely advanced age, older than the supposed age of the universe. For scientists, this was a double shock. First, it challenged the reliability of stellar age dating methods. If these methods could produce a figure that exceeded the universe's age, perhaps they were systematically overestimating the ages of other stars as well. Second, it raised a more radical question. Could our age of the universe be wrong? Some cosmologists even toyed with the idea that perhaps the universe was older than 13.8 billion years, though this view was in direct conflict with the high-precision CMB data and other cosmological measurements like Type Ia supernova distances and the Hubble constant. These latter measurements painted a remarkably consistent picture of a universe born in a hot, dense state 13.8 billion years ago, expanding ever since. The tension between the two numbers, 16 billion years for a star and 13.8 billion years for the universe, forced astronomers to go back and scrutinize every step of the process. Could the star's distance have been slightly off? Even a small error here would change its calculated luminosity and therefore its age. Could the chemical abundance measurements be skewed by atmospheric interference or instrument limitations? Could the models themselves, which simulate stellar evolution, be missing some subtle physics? And there was a bigger philosophical question lurking in the background. If one seemingly ordinary star could threaten to topple the standard cosmological model, what else might be out there that we simply haven't discovered yet? This puzzle had all the hallmarks of great science: a solid observation, a clear contradiction with established theory, and a range of possible solutions, each of which could lead to new insights about the cosmos. For years, the Methuselah Star's impossible age was both a tantalizing mystery and a cautionary tale about the limits of our measurement techniques. It pushed astronomers to refine their tools and sharpen their models, ultimately leading to a far more precise understanding of both the star and the universe itself. In the end, that 16 billion year figure didn't survive unchanged. But in challenging it, scientists learned more about how to measure cosmic distances, how to model stellar interiors, and how to handle uncertainties in ways that improved our entire framework for understanding the oldest stars. In cosmology, the age of the universe acts like a cosmic speed limit. Nothing inside it can be older than the universe itself. That's why the Methuselah Star's early estimated age of 16 billion years wasn't just an odd curiosity. It was a direct contradiction of one of the most fundamental pillars of modern astrophysics. The standard cosmological model, the CDM model, lambda cold dark matter, is built on a framework that ties together the Big Bang, the cosmic expansion rate, the composition of matter and energy, and the structure of the universe on large scales. It has been reinforced by decades of observational evidence, from the cosmic microwave background to galaxy surveys. In this model, the 13.8 billion year age of the universe is not a loose guess. It's a highly constrained value derived from independent measurements that all converge on roughly the same number. If a single star were truly older than 13.8 billion years, there are only a few possibilities. 1. The star's age estimate is wrong. This is the most likely scenario when science encounters an anomaly. Our methods of measuring stellar ages rely on models that simulate the physics inside stars, nuclear fusion rates, convection, opacity of stellar material, etc., and any inaccuracies in those models could yield an incorrect age. 2. The age of the universe is wrong. This would mean something is deeply off in our cosmological calculations, such as the Hubble constant, the rate of cosmic expansion, the assumed makeup of dark matter and dark energy, or the physics governing the early universe. If that were true, it would require a sweeping revision of our most trusted theories. 3. Physics as we know it is incomplete. A less likely but fascinating possibility is that the star's apparent age points to new physics, unknown mechanisms in stellar evolution, an entirely different kind of formation history, or even something exotic about time measurement in the early universe. For cosmologists, this was a big deal because anomalies can be gateways to breakthroughs. The entire field thrives on identifying small inconsistencies that can lead to major leaps in understanding. The fact that Methuselah appeared to be older than the universe meant that, at least in principle, one of our best tested theories could be flawed, or our understanding of stellar aging needed a serious overhaul. The stakes were high because the CDM model doesn't just describe the age of the universe, it underpins our understanding of dark energy, dark matter, galaxy formation, and even the ultimate fate of the cosmos. If that framework had to be adjusted to make room for a star older than the universe, the ripple effects would touch nearly every branch of astrophysics. And here's the subtle danger in this kind of discrepancy. If we were willing to simply ignore the Methuselah Star because it didn't fit, we'd risk falling into the trap of protecting theory at the expense of observation. Science demands that if the data doesn't fit the theory, we either recheck the data carefully or start rethinking the theory itself. In this case, the Methuselah Star forced both. Astronomers improved their measurements and refined their theoretical models in response to the challenge. So, the problem in cosmology was simple in statement but enormous in implication. If the star's 16 billion year age were accurate, then either our understanding of stars or our understanding of the universe was fundamentally wrong. Stellar age dating might sound like something straight out of an intergalactic matchmaking service, but in astronomy, it's the serious business of figuring out how old a star really is. Unlike living things on Earth, stars don't come with birth certificates or Turing-like markers that you can count. Instead, astronomers have to piece together a star's biography from its physical properties, its brightness, color, chemical composition, and position on the Hertzsprung-Russell diagram, HR diagram. The process is part detective work, part physics, and part statistical modeling. At its heart, stellar age dating relies on the fact that stars change in predictable ways over time. A star's mass determines how fast it burns through its nuclear fuel, and its initial chemical composition influences how it evolves. By comparing a star's observed characteristics with theoretical models of stellar evolution, astronomers can estimate how long it's been shining. Here's the basic roadmap for how this works. 1. Measuring a star's brightness and temperature. Astronomers start by determining how bright the star appears from Earth, its apparent magnitude, and how far away it is. Using the star's distance, they can calculate its absolute magnitude, its intrinsic brightness, or how bright it would appear if placed exactly 10 parsecs, about 32.6 light-years, away. The star's color or spectrum tells us its surface temperature. Bluer stars are hotter and generally younger, unless they're in a late, massive star phase, while redder stars are cooler and often older. 2. Plotting it on the Hertzsprung-Russell diagram. The HR diagram is a kind of family portrait for stars, plotting luminosity against temperature. Most stars lie along the main sequence, a diagonal band where stars spend the bulk of their lives burning hydrogen into helium. Stars move off the main sequence when their core hydrogen runs out. Where a star falls on the diagram gives strong hints about its evolutionary stage, and thus, its age. 3. Using stellar evolution models. Stellar models simulate how stars of different masses and compositions change over time. They incorporate well-understood physics, nuclear fusion rates, energy transport inside the star, the effects of gravity and pressure, and the star's opacity, how transparent it is to radiation. By matching a star's observed temperature, luminosity, and chemical composition to a model, astronomers can estimate how long it has been evolving since its formation. 4. Considering metallicity, chemical composition. Metallicity refers to the fraction of a star's mass made up of elements heavier than helium. Astronomers measure metallicity through spectroscopy, analyzing the absorption lines in a star's light. A low metallicity means the star formed early in the universe's history, before many heavy elements existed. High metallicity means the star formed later, after generations of stars had enriched the cosmos with metals through supernova explosions. A metallicity doesn't give an exact age, but it sets strong constraints. If a star has extremely low metallicity, it's almost certainly ancient. 5. Using nuclear clocks. Some stars contain trace amounts of radioactive elements like thorium and uranium, which decay at known rates. By measuring the ratios of these isotopes to stable ones, astronomers can get an independent age estimate. This method, called nucleocosmochronology, works a bit like radiocarbon dating for stars. 6. Cluster dating versus single-star dating. For star clusters, the process is easier. Astronomers look for the turn-off point on the HR diagram where stars leave the main sequence. All stars in a cluster formed roughly at the same time, so the turn-off point tells the cluster's age. For isolated stars like Methuselah, it's trickier because you can't compare it to a group of peers. You have to rely on precise measurements and robust models. The key thing about stellar age dating is that it's model-dependent. The more accurate our physics and the better our data, the better the age estimate. But small uncertainties in temperature, luminosity, metallicity, or distance can lead to large differences in the calculated age. This is exactly why the Methuselah Star caused such a stir. Its observed properties, when first measured, plugged into the models and spat out an age that seemed impossible. In the case of HD 140283, early measurements of its distance and brightness, combined with its extremely low metallicity, placed it far along the subgiant branch on the HR diagram, implying it had been evolving for nearly the full age of the universe, or slightly more, depending on the assumed cosmological parameters. Later refinements in distance measurements would shift its position on the diagram just enough to shave off hundreds of millions of years from its calculated age, bringing it into line with the universe's timeline. So, stellar age dating isn't about finding one magic measurement. It's about weaving together many strands of data into a coherent life story for the star. And when the star in question is as old and unusual as Methuselah, every thread matters. Metallicity is one of the most powerful clues astronomers have when it comes to determining a star's age, especially for ancient stars like the Methuselah Star. In astronomy, metals is a catch-all term for any element heavier than helium, regardless of whether it's something we'd call a metal in everyday language. That means in the astronomical sense, oxygen, carbon, nitrogen, silicon, iron, and even gold are all metals. Why does this matter for age dating? Because the universe wasn't born with these heavier elements. Right after the Big Bang, the cosmos was almost entirely hydrogen, about 75% by mass, and helium, about 25%, with trace amounts of lithium. All other elements, the oxygen you breathe, the iron in your blood, the calcium in your bones, were forged later, in the nuclear furnaces of stars and in the cataclysmic explosions of supernovae. This means that the first generation of stars, called population 3 stars, were almost pure hydrogen and helium. They lived fast, burned bright, and died quickly, seeding the cosmos with heavier elements. The second generation of stars, population 2, formed from gas clouds that had been slightly enriched with those elements. Over cosmic time, successive generations of stars kept enriching the interstellar medium, so younger stars, population 1 stars, like our Sun, were born with far higher metallicities. How metallicity works as an age clue. When astronomers measure a star's metallicity, they essentially take its chemical fingerprint. This is done through spectroscopy, where the star's light is split into a spectrum and examined for dark absorption lines. These lines occur at very specific wavelengths depending on which elements are present in the star's atmosphere. By measuring the strength of these lines, scientists can determine how much of each element the star contains compared to hydrogen. Metallicity is usually expressed relative to the Sun's metallicity in a logarithmic scale called FeH, iron to hydrogen ratio. For example, RFeOH equals 0.0 means the star has the same iron to hydrogen ratio as the Sun. RFeH equals -1.0 means the star has 1/10 the Sun's iron abundance. RFeH equals -2.0 means it has 1/100 the Sun's iron abundance. RFeH equals -3.0 means 1,000th, and so on. The Methuselah Star's metallicity is extraordinarily low, around FeH equals -2.4, meaning it is only about 1/250th of the Sun's iron abundance. This is a screaming signal that it formed in the very early universe, before heavy elements had much time to accumulate. It likely formed just after the first generation of stars had exploded and scattered their fusion products into space. Why metallicity matters for age calculations. Low metallicity doesn't tell you the exact age, but it narrows the range dramatically. If a star has extremely low metallicity, it must be ancient because the interstellar medium it formed from was barely enriched. Conversely, high metallicity stars are almost certainly younger, having formed after many stellar generations had already seeded the galaxy with metals. In practice, metallicity plays two key roles in stellar age estimates. 1. Constraining the formation epoch. Metal-poor stars must have formed within the first billion years or so after the Big Bang. This sets a hard upper limit on their age, basically as old as possible without exceeding the universe's age. 2. Affecting stellar evolution models. Metallicity changes the way a star evolves. Metals in a star's atmosphere increase opacity, how much light is trapped inside, which affects how energy flows through the star and thus its temperature, luminosity, and lifetime. Metal-poor stars are generally hotter and bluer at a given mass, and they evolve differently than metal-rich stars. That means if you don't get the metallicity right, your stellar models, and thus your age estimate, can be significantly off. The Methuselah Star's metallicity as a cosmic clue. HD 140,283's very low metallicity immediately flagged it as one of the Milky Way's oldest residents. In fact, its chemistry doesn't just show low iron, it also has unusual ratios of other elements, like oxygen and magnesium, that hint at the types of supernovae that enriched its birth cloud. These patterns suggest it may have formed from material enriched by just one or two earlier supernovae from massive population 3 stars. Because metallicity is so critical, it was one of the first measurements astronomers rechecked when Methuselah's age seemed to overshoot the age of the universe. Improved spectroscopy confirmed that its metallicity is indeed extremely low, supporting the idea that it's among the galaxy's firstborn. In essence, metallicity is the fossil record of a star's birth environment. It tells us not just when the star might have formed, but also what the universe was like at the time, what elements existed, how many earlier stars had lived and died, and how enriched the cosmic gas had become. For Methuselah, that record says loud and clear, "I was born in the universe's earliest days, when the cosmos was still young, raw, and almost entirely made of hydrogen and helium." The Methuselah Star's extraordinarily low metallicity is more than just a chemical curiosity. It's a direct window into the early universe and one of the clearest reasons astronomers believe it's among the oldest stars in existence. To understand why, we have to rewind the cosmic clock to the very first few 100 million years after the Big Bang, when the universe was a radically different place. The primordial universe and the first stars. In the moments after the Big Bang, the universe was too hot and dense for atoms to exist. As it expanded and cooled, protons and electrons combined to form hydrogen, with some helium and trace lithium. No heavier elements existed, no carbon, oxygen, iron, or gold. These heavier elements, what astronomers call metals, had to be created later, inside stars. The first generation of stars, population 3 stars, were born from this pristine hydrogen-helium mix. They were massive, short-lived, and incredibly hot, burning through their nuclear fuel in just a few million years before exploding as supernovae. Those explosions seeded their surroundings with the first tiny amounts of heavier elements. The next generation, population 2 stars, formed from gas clouds that had been slightly enriched by these early supernovae. Their metallicities were extremely low because only a few earlier stars had contributed to the chemical mix. Methuselah belongs to this generation. Its chemistry records a time when the universe had only just begun its journey toward chemical complexity. How metallicity marks extreme age. Because the amount of metals in the galaxy increases steadily over time, as more stars live and die, a star's metallicity is like a timestamp. The lower the metallicity, the earlier the star must have formed, up to the limit of the universe's age. Here's why Methuselah's FeH, almost equal to -2.4, about 1/250th the Sun's iron content, is such a big deal. 1. The enrichment timeline. By the time our Sun formed 4.6 billion years ago, the galaxy was already rich in metals from billions of earlier supernovae. Stars with Sun-like or higher metallicity formed in relatively recent cosmic history. For a star to have such low metallicity, it must have formed before this heavy enrichment had taken place, meaning it had to be born very early in the Milky Way's history, likely within the first billion years of its existence. 2. Minimal pollution. Even ancient stars can sometimes have their atmospheres contaminated by material from nearby stars, which can artificially boost their measured metallicity. Methuselah's spectrum shows no significant signs of this kind of contamination. Its chemical fingerprint is consistent with having been untouched since its birth. 3. Supernova fingerprint. The ratios of different elements in Methuselah reveal that it was enriched by very few supernovae, probably 1 or 2 massive stars that exploded before it formed. This is a hallmark of extreme age, because later stars formed from gas that had been mixed and remixed by countless generations of stellar deaths. Why this points to the earliest era of star formation. If we place Methuselah on the cosmic timeline, it almost certainly formed when the Milky Way was still in its infancy, or possibly before the Milky Way fully coalesced. Its low metallicity is so extreme that it pushes it back to a time when there had been barely any star formation at all. That makes it a galactic fossil, a survivor from an age when the conditions in the universe were unlike anything we see today. It's worth noting that there are other metal-poor stars in the galaxy, some with even lower metallicity than Methuselah. But most of those are much farther away, and we can't study them in the same detail. Methuselah is rare because it's both extremely old and unusually close to us, about 190 light-years away, which lets us measure its properties with far greater precision. The metallicity-age connection in stellar models. Low metallicity doesn't just hint at a star's age, it actively changes how we calculate it. Metal-poor stars have different opacities, how easily photons can escape from their interiors, compared to metal-rich stars. This affects their temperatures, luminosities, and rates of nuclear fusion. If you take a star's metallicity into account when plugging its properties into stellar evolution models, you get a more accurate age estimate. For Methuselah, the combination of a low metallicity, a subgiant evolutionary stage, and precise distance measurements places it right at the edge of what's physically possible for stellar ages, just slightly younger than the universe itself when uncertainties are considered. In short, Methuselah's metallicity isn't just a random number, it's a chemical time capsule. It tells us that the star was born in the universe's youth, before heavy elements became common, making it one of the oldest stars we can directly observe. That's why scientists treat it not just as a nearby curiosity, but as a crucial piece of evidence for understanding how the earliest stars lived and died, and how galaxies like ours came to be. High metallicity and low metallicity stars might look similar through a telescope. Both are points of light, but chemically and historically, they belong to very different chapters in the universe's story. Their metallicity tells astronomers not only about their age but also about the kind of cosmic environment they were born into. Understanding the difference is key to seeing why the Methuselah Star stands out as such a remarkable relic. High metallicity stars. These are the new kids on the block in cosmic terms, though new might still mean billions of years old. 1. Definition. A high metallicity star has a relatively large fraction of its mass in elements heavier than helium, the metals in astronomical language. In the FeH scale, high metallicity stars often have values close to or greater than 0.0, meaning they have similar or higher iron abundance than the Sun. 2. Formation era. High metallicity stars form after many generations of stars have lived and died, enriching the interstellar medium with metals via supernova explosions and stellar winds. By the time our Sun formed about 4.6 billion years ago, the Milky Way's gas was already heavily polluted with these elements, so the Sun and its planetary system are relatively metal-rich. 3. Appearance and evolution. High metallicity stars tend to have more complex spectra, with stronger absorption lines from metals like iron, calcium, sodium, and magnesium. The higher metal content affects their opacity, making them slightly cooler and redder for a given mass compared to their low metallicity counterparts. 4. Planet formation link. There's a strong observed correlation between high metallicity and the likelihood of hosting planets, especially gas giants. More metals in the protoplanetary disk means more solid material to build planetary cores. That's why planetary systems are common around Sun-like stars but are rare around extremely metal-poor stars. 5. Examples. The Sun, Alpha Centauri A and B, and most stars you see with the naked eye fall into the high metallicity category because they're part of the Milky Way's thin disk, which is relatively young and metal-rich. Low metallicity stars. These are the ancient elders of the galaxy, fossils from a time before the universe was chemically diverse. 1. Definition. Low metallicity stars have a very small fraction of metals compared to hydrogen and helium. On the FeH scale, they might be at -1.0, -2.0, or even lower. Methuselah's FeH is about -2.4, meaning it has just 1/250th the Sun's iron content. 2. Formation era. Low metallicity stars were born early in the galaxy's history, sometimes just after the first supernovae seeded the cosmos with trace metals. The earliest low metallicity stars are known as population 2 stars, old but not quite pristine like the hypothetical population 3 stars. 3. Appearance and evolution. Their spectra are far simpler, with weak metal absorption lines, because their atmospheres lack significant amounts of heavy elements. For a given mass, low metallicity stars are generally hotter and bluer than high metallicity stars, due to their lower opacity allowing radiation to escape more easily. 4. Planet formation link. Planetary systems are rare around low metallicity stars. There simply wasn't enough heavy material in their birth clouds to form rocky planets or large planetary cores. If planets do exist around such stars, they're likely to be unusual and possibly metal-poor themselves. 5. Examples. Stars in the galactic halo and in ancient globular clusters, like those in Omega Centauri or M13, are typically low metallicity. Methuselah, being a nearby halo star, is a prime example. Some extremely metal-poor stars have been found with FeH below -5.0, meaning they have less than 1/100,000th the Sun's iron abundance, likely formed from almost pristine gas. Why this distinction matters for Methuselah. The difference between high and low metallicity stars is like the difference between a modern skyscraper made of steel and glass and an ancient stone monument. Both are buildings, but one reflects a time when construction materials and techniques were limited, while the other benefits from centuries of technological progress. Methuselah's low metallicity firmly anchors it in a primitive epoch of star formation. It's essentially a stone monument from the dawn of the galaxy, built with the simplest cosmic materials, untouched by the chemical richness that would come later. Quick comparison table. Feature: high metallicity star, low metallicity star. Typical age: young to middle-aged, 0 to 8 billion years. Very old, 8-13+ billion years. FeH, value near 0.0 or positive -1.0 or lower. Birth environment: metal-rich gas clouds in galactic disk, metal-poor gas in early halo or dwarf galaxies. Opacity: higher, cooler for given mass, lower, hotter for given mass. Planetary systems: common, often complex, rare, if any planets form. Example: the Sun Methuselah Star, HD 140283. In the case of the Methuselah Star, its low metallicity isn't just a note in a data table. It's the fingerprint of a star that formed before the Milky Way was fully assembled, likely from gas touched by only a handful of earlier stars. That's why its age estimate edges so close to the age of the universe itself. The Hubble Space Telescope, HST, played a pivotal role in unraveling the mystery of the Methuselah Star's seemingly impossible age. Without Hubble's exceptional precision, astronomers might still be scratching their heads over whether HD 140283 could really be older than the universe. The reason Hubble was so crucial comes down to two intimately connected factors in stellar astrophysics: distance and luminosity. Why distance matters for age estimates. To estimate a star's age, astronomers don't just look at its color or spectrum. They need to know where it sits on the Hertzsprung-Russell (HR) diagram, which plots stars' brightness against their temperature. This position tells you what stage of its life cycle the star is in, and that's the starting point for age modeling. Here's the catch: brightness is tricky. We see a star's apparent brightness from Earth, but what we really need is its intrinsic brightness, or luminosity, how much light it's actually putting out. If you don't know the star's exact distance, you can't tell whether it's truly faint or just far away. Even a small error in distance can lead to big errors in luminosity, which then cascade into the age calculation. How Hubble improved the measurement. The most reliable way to measure stellar distances is the parallax method, watching how a star appears to shift against the background of more distant stars as Earth orbits the Sun. The size of this tiny shift, measured in arcseconds, is directly related to the star's distance. Ground-based telescopes can measure parallax, but Earth's atmosphere distorts incoming light, blurring the images and limiting accuracy. The Methuselah Star's parallax shift is incredibly small, less than 18 milliarcseconds, which is like measuring the width of a human hair from several kilometers away. For such tiny angles, atmospheric interference is a serious obstacle. That's where Hubble's Fine Guidance Sensors, FGS, came in. The FGS is normally used to keep Hubble precisely pointed at its targets, but it can also serve as a super-accurate astrometer, measuring positions of stars to an accuracy of about 0.2 milliarcseconds. From 2003 to 2011, astronomers used Hubble's FGS to repeatedly observe HD 140283, tracking its position relative to background stars over multiple years. Results of Hubble's parallax campaign. Hubble's observations yielded an exceptionally precise parallax for Methuselah, which translated to a distance of about 190 light-years, or 58 parsecs. This wasn't just a nice-to-know number, it allowed astronomers to pin down the star's luminosity with unprecedented accuracy. With luminosity locked in, they could place Methuselah's data point precisely on the HR diagram and match it to stellar evolution models that accounted for its metallicity and temperature. This was a huge step toward refining its age. Why luminosity precision is so critical. Stellar models are sensitive to luminosity because it tells you how far along the star is in burning its fuel. Methuselah is a subgiant, meaning it has exhausted the hydrogen in its core and is beginning to swell and brighten as it evolves toward the red giant phase. The rate at which a star becomes a subgiant depends on its mass, composition, and fusion history. If you know the star's luminosity with high confidence, you can reverse engineer its life story and estimate how long it's been shining. A luminosity uncertainty of even 2 to 3% can shift the age estimate by hundreds of millions of years. Before Hubble, those errors were large enough that Methuselah's age estimates could swing wildly, sometimes pushing beyond the universe's age. Hubble's sharp data slashed that uncertainty dramatically. Why Hubble was the perfect tool for the job. Hubble's advantage wasn't just precision, it was stability. Because it orbits above Earth's atmosphere, it avoids distortion and light scattering, providing clean, consistent data. Over the 8 years of observations, that stability allowed for a parallax measurement that ground-based observatories couldn't match at the time. This is a great example of how the Hubble Space Telescope isn't just for taking pretty pictures of nebulae and galaxies. It's also an incredibly powerful tool for high-precision measurements that directly impact fundamental cosmological questions. Thanks to Hubble, astronomers could say with confidence that Methuselah is indeed extremely old, but not definitively older than the universe, once all sources of error were taken into account. The result narrowed its age from an eyebrow-raising 16 billion years down to a range that overlaps with the universe's 13.8 billion years, putting the mystery into the realm of intriguing but explainable. Uncertainties in distance measurements are like a subtle but dangerous ripple effect in stellar astrophysics. Small errors in one measurement can snowball into wildly different conclusions about a star's history, especially when it comes to age. In the case of the Methuselah Star, the mystery of whether it was older than the universe itself hinged almost entirely on just how precisely we could measure how far away it really is. From distance to brightness, the first link in the chain. When astronomers look at a star, the first thing they can measure directly is its apparent magnitude, how bright it seems from Earth. But a star's true luminosity, the total amount of light it emits, depends on how far away it is. \text, luminosity, equals \text, apparent brightness, \times. 4\pi times \text, distance, ⁻2. If the distance is overestimated, the star's calculated luminosity will be too high. If underestimated, the luminosity will come out too low. This is the first place where small errors in distance cause big shifts in derived properties. From brightness to life stage. Once luminosity is known, astronomers can plot the star on the Hertzsprung-Russell diagram alongside its color or temperature. This diagram acts like a stellar life chart, showing whether a star is on the main sequence, still burning hydrogen in its core, a subgiant, just finished core hydrogen burning, a red giant, expanding as core helium burning approaches. Methuselah is a subgiant. The exact point where it sits on the diagram tells us how much time has passed since it formed. But here's the catch: shift its luminosity slightly, because of a distance error, and it might appear higher or lower on the diagram, making it seem older or younger than it actually is. Why this is amplified for old stars. For stars near the upper edge of possible stellar ages, like Methuselah, the luminosity-age relationship is steep. That means a small change in luminosity corresponds to a big change in age. For example, if luminosity is overestimated due to a small distance overestimation, the star appears to be further along in its evolution, possibly suggesting it's older than it really is. If luminosity is underestimated, the star appears younger. Before Hubble refined Methuselah's parallax measurement, the error bars were large enough that the derived age could swing by 1 billion years or more, enough to place it either comfortably younger than the universe or alarmingly older than it. A real-world analogy. It's a bit like trying to guess someone's age based on how tall they are, without knowing whether they're standing on tiptoe or on a step. Even a few centimeters of misjudgment can lead you to think they're several years older or younger than they really are, especially if they're already near the maximum expected height for their age group. For Methuselah, we're talking about a star already close to the universe's age limit, so every centimeter matters. The Hubble correction. When ground-based parallax measurements had uncertainties of around 10% or more for Methuselah, this translated into massive uncertainty in luminosity and thus age. Hubble's fine guidance sensors reduced the parallax error to a fraction of a milliarcsecond, cutting the distance uncertainty to less than 2%. This seemingly tiny improvement narrowed the possible age range dramatically, moving Methuselah from older than the universe to just barely younger, within the margin of error. The chain of dependency. Here's the full cause and effect chain that distance uncertainty triggers. 1. Parallax error. 2. Distance error. 3. Luminosity error. 4. Incorrect HR diagram position. 5. Misidentified evolutionary stage. 6. Flawed stellar model fit. 7. Inaccurate age estimate. Methuselah's case is a textbook example of how, in astronomy, even a small observational uncertainty can ripple forward into a cosmic scale puzzle. Without precise distance measurements, Methuselah might still be carrying the misleading reputation of the star that's older than the universe. Thanks to improvements from Hubble and later missions like Gaia, we've pushed that uncertainty down to a level where the numbers make physical sense, though the star remains a record-breaking elder by almost any standard. The parallax method is the cornerstone of measuring distances to nearby stars, and in astronomy, getting the distance right is the first step to understanding almost everything else about a star. Without an accurate distance, you can't accurately determine a star's true brightness, its size, or even where it is in its evolutionary life cycle. For a star like Methuselah, which sits on the knife's edge of the universe's age, parallax is the difference between a plausible history and a cosmic contradiction. What is parallax? Parallax is a simple concept. If you hold your finger in front of your face and close one eye, then switch eyes, your finger seems to jump against the background. The shift happens because each eye sees the world from a slightly different position. Astronomers use Earth's orbit as a giant baseline for the same effect. By taking precise measurements of a star's position 6 months apart, when Earth is on opposite sides of the Sun, they can detect a tiny apparent shift against the much more distant background stars. This shift is measured in arcseconds, where 1 arcsecond equals 1/600 of a degree. For context, the Moon's diameter is about 1,800 arcseconds across, so we're talking about incredibly small angles. Why it's so important? Parallax is the only direct method we have for measuring stellar distances. Every other method, like spectroscopic parallax, main sequence fitting, or using Cepheid variable stars, depends on calibrations that ultimately trace back to parallax measurements. It's the bedrock of the cosmic distance ladder. For nearby stars, within a few hundred light-years, parallax gives distances that are not just reliable, but also free from many of the assumptions and modeling uncertainties that affect other methods. This is crucial for calibrating all of astrophysics. Challenges with parallax for Methuselah. Methuselah's parallax angle is less than 0.018 arcseconds, 18 milliarcseconds. That's equivalent to spotting the width of a human hair from about 10 kilometers away. Measuring such a tiny angle pushes the limits of both technology and methodology. A ground-based telescope struggles because Earth's atmosphere blurs and shifts starlight. Even with adaptive optics, the atmosphere's turbulence adds noise. An instrumental drift and reference star motion must be accounted for. Nearby stars also have their own motions across the sky. A long-term tracking is essential to distinguish parallax shifts from a star's own proper motion. Methuselah is a halo star moving rapidly relative to the Sun, so its proper motion is huge, over 1 arcsecond per year, dwarfing its parallax signal. It's like trying to detect a small wiggle in a speeding race car while it's zooming past you. Hubble's fine guidance sensors and parallax accuracy. The Hubble Space Telescope's fine guidance sensors, FGS, were game-changers for Methuselah's parallax. Above Earth's atmosphere, Hubble could track the star's position relative to background objects with unprecedented stability. Over 8 years of observations, Hubble reduced the distance uncertainty from 10% to under 2%. For Methuselah, that difference was monumental. At the old uncertainty level, the age estimates could swing wildly, sometimes implying 16 billion years, sometimes under 13 billion. The refined parallax allowed astronomers to place it much more securely on the HR diagram, tightening the age range to around 14.27 billion years, with a margin of error small enough to overlap with the universe's age. From parallax to cosmic understanding. Parallax isn't just about Methuselah. It's the yardstick that underpins much of our knowledge about the universe. Once you have accurate distances for nearby stars, you can calibrate luminosities for various spectral types, anchor stellar evolution models, test cosmological parameters by checking if stellar ages align with the age of the universe, refine the scale of the Milky Way itself. In a way, parallax is astronomy's equivalent of having a ruler that measures the first rungs of a ladder. If that ruler is off, the whole ladder wobbles. For Methuselah, the parallax method didn't just give us a number, it gave us a lifeline. To pull the star's age back into the realm of physical possibility. Without it, we might still be staring at data that stubbornly claimed a star could be older than time. When astronomers estimate the age of a star like Methuselah, they aren't looking at a giant cosmic clock ticking away in the background. They're inferring its age from our understanding of how stars evolve over time, and that understanding rests heavily on nuclear fusion rates and the stellar models built around them. These two factors determine how quickly a star moves through its life stages and therefore how old it appears when we observe it today. Nuclear fusion, the engine that drives stellar aging. Stars shine because of nuclear fusion, the process by which lighter atomic nuclei combine to form heavier ones, releasing vast amounts of energy. In the cores of most stars, including Methuselah in its youth, hydrogen nuclei, protons, fused into helium via the proton-proton chain. This process converts a small fraction of the star's mass into energy, following Einstein's famous equation E equals mc squared. The rate at which fusion happens depends on 1. Core temperature. Higher temperatures make fusion occur faster. 2. Star's mass. More massive stars have hotter cores, so they burn fuel faster and have shorter lifespans. 3. Chemical composition, metallicity. Elements heavier than helium affect how energy moves through the star, influencing core temperature and pressure. Methuselah is low mass and extremely low in metals, meaning it burns fuel more slowly than a star like our Sun. That slow burn is one reason it could survive for nearly the age of the universe itself. From fusion rates to age estimates. When a star exhausts hydrogen in its core, fusion shifts outward into a shell surrounding a helium core. This causes the star to expand and brighten. It moves off the main sequence into the subgiant stage. The point at which this happens, and how quickly it progresses, is predictable if you know the star's mass and composition. For Methuselah, astronomers can measure a temperature from its spectrum, a luminosity from distance plus apparent brightness, a metallicity from spectral lines. These parameters are fed into stellar evolution models, which simulate the star's entire life from formation to death, step by step, based on fusion physics. By matching Methuselah's current observed properties to a point in these simulated life histories, astronomers can estimate its age. How metallicity changes fusion efficiency. Methuselah's extremely low metallicity means its core's opacity, resistance to the flow of photons, is low. This allows energy to escape more easily, subtly altering the star's internal pressure and temperature balance. In turn, this affects the fusion rate. Low metallicity stars burn hydrogen differently than metal-rich stars like the Sun. For age determination, this is vital. If you assumed Methuselah had the Sun's metallicity, you'd calculate a much younger age than reality. This is why metallicity is explicitly built into stellar models, and why getting it wrong can skew the age by billions of years. The role of stellar models. Stellar models are complex simulations that solve equations for a hydrostatic equilibrium, gravity pulling in versus pressure pushing out, energy generation, nuclear fusion, energy transport, radiation or convection, a mass loss over time. These models incorporate nuclear reaction rates measured in particle accelerators, laboratory plasma experiments, and quantum mechanical calculations. Any uncertainty in these rates, especially at the low energies found in stellar cores, translates into uncertainty in age estimates. Why fusion rate precision matters so much for Methuselah. Methuselah's possible age is right up against the cosmic limit of 13.8 billion years. Even a 1% change in assumed fusion efficiency in the models could shift its calculated age by hundreds of millions of years. This is why early models that didn't account for some effects, like updated opacities, diffusion of elements in the star's interior, and revised nuclear cross-sections, could produce unrealistic 16 billion year ages. When updated nuclear reaction rates were included, especially for the proton-proton chain and helium production, Methuselah's estimated age dropped to a value more in line with the universe's age, even without changing its observed properties. Fusion as the clock mechanism. You can think of a star's fusion rate as the ticking mechanism of a cosmic clock. Faster fusion equals the clock runs fast and the star ages quickly. Slower fusion equals the clock ticks slowly and the star can last billions of years longer. Methuselah's low mass and low metallicity made its clock extremely slow, allowing it to shine steadily since just after the universe began. Without nuclear fusion physics and stellar models to interpret it, we'd have no way of turning Methuselah's brightness and spectrum into an actual age. And without refining those models over decades, we'd still be faced with a star that looked older than the cosmos. The story of Methuselah's age is a fascinating example of how science is a self-correcting process. Early measurements suggested a paradox. This star seemed older than the universe itself, but with new data and improved models, astronomers were able to revise its age downward, resolving the apparent conflict. This journey highlights the interplay between observation, theory, and technological advancement. Early age estimates and the paradox. In the late 1990s and early 2000s, observations of Methuselah, based primarily on ground-based parallax measurements and preliminary stellar models, suggested an age of roughly 16 billion years. This was alarming because the Big Bang cosmology, refined by measurements of the cosmic microwave background, CMB, indicated that the universe itself is only 13.8 billion years old. This discrepancy posed a serious problem. How could a star exist that is older than the very universe it inhabits? At first, this seemed almost impossible and raised doubts about the reliability of either the stellar age dating methods or the cosmological parameters. Identifying the sources of error. Astronomers quickly realized that several factors could be causing Methuselah's apparent overage. 1. Distance uncertainties. Ground-based parallax measurements had significant error margins. Small errors in distance translate into large errors in luminosity, which then propagate into age estimates. 2. Stellar model limitations. Early models did not fully incorporate the effects of element diffusion, updated opacities, or revised nuclear reaction rates. These could artificially inflate the star's age when interpreted through the models. 3. Metallicity measurement uncertainties. While it was clear Methuselah was extremely metal-poor, the exact abundance of elements heavier than helium was crucial in accurately modeling its evolution. Slight misestimates could shift the star's predicted age by billions of years. Refinement through new data. The first major breakthrough came with the Hubble Space Telescope, HST. Using its fine guidance sensors, astronomers measured Methuselah's parallax with far greater precision than had been possible from the ground. Hubble reduced the distance uncertainty to under 2%, which had an immediate effect on the age estimate. With a more accurate distance, the star's luminosity could be measured reliably, placing it more precisely on the Hertzsprung-Russell diagram. Around the same time, advances in stellar spectroscopy provided better measurements of the star's metallicity and chemical composition. This allowed models to reflect more accurately the conditions in Methuselah's interior. Advances in stellar modeling. Parallel to observational improvements, theorists refined stellar evolution models. Key improvements included: 1. Diffusion of elements. Stars are not perfectly static. Heavier elements gradually sink toward the core over billions of years. Accounting for this effect changes how a star's surface temperature and luminosity evolve. 2. Updated nuclear reaction rates. Laboratory measurements of proton-proton chain reactions and helium fusion reactions were incorporated, giving more accurate lifetimes for low-mass, metal-poor stars. 3. Opacities and energy transport. Improved understanding of how radiation and convection transfer energy in metal-poor stars allowed models to predict more realistic surface temperatures and luminosities. Together, these refinements meant that Methuselah's age no longer appeared unreasonably high. Combining new data with models. By combining Hubble's precise parallax measurements with updated models, astronomers recalculated Methuselah's age at about 14.27 billion years, with a margin of error of approximately plus or minus 0.8 billion years. This is slightly younger than the universe, but still extremely old, placing it among the first generation of stars formed after the Big Bang. The downward revision resolved the paradox. Methuselah was no longer older than the universe. Instead, it became a remarkable witness to nearly the entire history of cosmic evolution, forming shortly after the first stars ignited. Timeline of age estimates. A brief look at the evolving age estimates illustrates the refinement process. A 1995 to 2000, 16 billion years, ground-based parallax, early models. A 2005, 15.3 billion years, preliminary Hubble measurements, revised metallicity. A 2012 to 2013, 14.27 plus or minus 0.8 billion years, Hubble fine guidance sensors, improved stellar models. Each iteration shows how improved observations and theoretical understanding brought the star's age into a physically plausible range. Significance of this revision. This revision process demonstrates two key points in astronomy. 1. The interplay between observation and theory. Neither alone could solve the paradox. Only by combining precise measurements with accurate models could astronomers reconcile Methuselah's age with the universe's age. 2. The importance of uncertainties. Early claims that Methuselah was older than the universe were technically possible within the margin of error, but careful measurement and modeling allowed that uncertainty to shrink, illustrating how scientific knowledge gradually converges toward reality. Methuselah thus transitioned from being a seeming cosmological challenge to becoming a cornerstone object for testing theories of stellar evolution, the formation of the early universe, and even the physics of the first generations of stars. Creating a timeline of Methuselah's age estimates provides a clear narrative of how astronomical techniques and models evolved, and how the apparent paradox of a star older than the universe was gradually resolved. Each point on this timeline reflects advances in observation, theoretical modeling, and our understanding of stellar physics. By examining this timeline, we can appreciate not only the history of Methuselah studies but also the broader evolution of cosmology as a science. Timeline of Methuselah Star age estimates. 1995 to 2000. Ground-based observations and early models. Estimated age. 16 billion years. Data sources. Ground-based telescopes measuring parallax and brightness. Early spectroscopic metallicity measurements. Stellar models, relatively simplistic, did not fully account for element diffusion or updated opacities. Context. This estimate implied Methuselah was older than the universe itself, 13.8 billion years, creating a dramatic paradox. The scientific community recognized this discrepancy but treated it cautiously, suspecting observational or modeling errors. 2001 to 2005. Preliminary Hubble observations. Estimated age. 15.3 billion years. Data sources. Early Hubble Space Telescope parallax measurements. Improved metallicity determinations. Stellar models, slightly more refined, some consideration of low metallicity effects on energy transport. Impact. The age estimate decreased slightly but still suggested an age older than the universe. This phase underscored the need for more precise distance measurements and better modeling. 2006 to 2011. Refined spectroscopy and stellar physics updates. Estimated age. 15 billion years. Data sources. High-resolution spectroscopy. Improved understanding of nuclear reaction rates and low metallicity stellar atmospheres. Stellar models. Incorporation of element diffusion and improved opacities. Better treatment of convection. Impact. Models now accounted for. Internal processes that slow apparent aging, narrowing the discrepancy with the universe's age. Methuselah was still extremely old but increasingly consistent with cosmological models within error margins. 2012 to 2013. Hubble Fine Guidance Sensor Precision Measurements. Estimated age. 14.27 plus or minus 0.8 billion years. Data sources. Long-term parallax monitoring by Hubble, extremely accurate distance measurement, 190 light-years, refined luminosity calculations. Stellar models. Advanced modeling of low metallicity stars, updated nuclear fusion rates, diffusion effects fully integrated. Impact. The age estimate firmly placed Methuselah slightly younger than the universe, resolving the age paradox. The margin of error allowed for overlap with the universe's 13.8 billion year age, providing a coherent cosmological picture. 2015 present. Ongoing refinement and model verification. Estimated age. 14.27 plus or minus 0.8 billion years, current best estimate. Data sources. Gaia mission data further refined distances for halo stars, ongoing spectroscopic and photometric observations. Stellar models. Continued adjustments based on new physics and cross-checking with other ancient stars. Impact. Methuselah is now a benchmark for testing stellar evolution, early star formation, and the conditions of the post-Big Bang universe. Its age aligns with cosmological parameters derived from the cosmic microwave background and large-scale structure studies. Graphical representation of the timeline. To visualize the evolution of age estimates, imagine a timeline along a horizontal axis representing years of study. Vertical markers indicate age estimates in billions of years. 16 asterisk, 15 asterisk, 14 asterisk, 13, 12 years, 1995 present. Asterisk marks key revisions in age estimates. Early markers, 16 billion, reflect ground-based uncertainty and model limitations. Later markers, 14.27 billion, reflect Hubble's precise parallax data and improved stellar models. This visualization shows a steady downward trend in estimated age as observational precision and theoretical modeling improved. Insights from the timeline. 1. Science is iterative. Each new dataset or modeling improvement nudged the age estimate closer to physical reality. 2. Small improvements matter. Even minor changes in distance or metallicity can shift age estimates by billions of years. 3. Integration of observation and theory. Observations alone couldn't resolve the age paradox. Theoretical understanding of fusion rates, element diffusion, and stellar structure was crucial. 4. Uncertainty persists. Even with the most advanced instruments, there remains a margin of error due to limits in modeling and observational precision. This is why Methuselah's age is reported as 14.27 plus or minus 0.8 billion years, rather than a single fixed number. Broader implications. The timeline highlights more than just Methuselah, it illustrates how astrophysics deals with extreme cases and tests the boundaries of knowledge. A star like Methuselah is both a challenge and a tool. A challenge, it initially seemed to contradict fundamental cosmological principles. A tool, by studying it carefully, astronomers refined stellar physics, distance measurement techniques, and cosmological parameters. It also demonstrates the incredible progress enabled by space-based telescopes. Without Hubble, and soon, next-generation observatories like the James Webb Space Telescope, this ancient star would remain a puzzle, potentially appearing to defy the universe itself. Current consensus on Methuselah's age provides both relief and awe. After decades of careful observation, modeling, and reanalysis, astronomers now place its age at roughly 14.27 billion years, with an uncertainty of about plus or minus 0.8 billion years. This estimate is slightly younger than the universe itself, which is measured at 13.8 billion years based on observations of the cosmic microwave background, large-scale structure, and expansion rates. While at first glance this may seem paradoxical, how can a star appear older than the universe? The inclusion of a margin of error resolves the tension and gives context to the precision limits of astrophysical measurements. Why 14.27 billion years is significant? Methuselah's age is extraordinary not just because it's close to the age of the universe, but because it places the star among the earliest objects to form in cosmic history. It likely emerged shortly after the first generation of stars ignited, making it a direct witness to the universe's infancy. At this age, Methuselah is practically a living fossil in the stellar population of our galaxy, offering a rare window into conditions shortly after the Big Bang. Understanding the margin of error. The plus or minus 0.8 billion years margin of error is crucial. Scientific measurements are never perfectly precise, and multiple factors contribute to uncertainty in a star's age. 1. Distance measurements. Even with Hubble's fine guidance sensors or Gaia data, parallax measurements have a small degree of uncertainty. A slight miscalculation in distance can lead to a significant shift in estimated luminosity, which affects the age derived from stellar models. 2. Stellar modeling limitations. Models of low metallicity, ancient stars like Methuselah involve assumptions about nuclear fusion rates, energy transport, and element diffusion. Small uncertainties in these processes propagate into age estimates. 3. Chemical composition measurements. Determining a star's metallicity to a high degree of accuracy is difficult. Since metallicity heavily influences stellar evolution rates, even minor errors can affect the calculated age. Because of these factors, astronomers cannot claim an exact number. Instead, the age is expressed as a best estimate plus or minus a range, reflecting the inherent uncertainties. Putting the age in context. Even at 14.27 billion years, Methuselah is still astonishingly old, being nearly as old as the universe itself. To give perspective, the Sun, a middle-aged star, is only 4.6 billion years old, roughly a third the age of Methuselah. A Methuselah formed at a time when galaxies were just beginning to take shape and when the first heavy elements were being produced by the earliest supernovae. Its low metallicity indicates that it formed in a universe dominated by hydrogen and helium, with almost no heavier elements, a stark contrast to stars forming in today's metal-rich galactic environment. Why the slight difference between the star and universe matters. At first, the early overestimate of 16 billion years caused concern because it seemed physically impossible. But with the refined age, we now see that Methuselah is slightly younger than the universe, just within the margin of error. This tiny difference is scientifically meaningful. 1. It confirms that stellar evolution models are largely correct when calibrated with precise observations. 2. It demonstrates that cosmological models, Big Bang, expansion rate, CMB measurements, are consistent with observations of ancient stars. 3. It highlights the limits of precision in measuring events that happened over 13 billion years ago, a reminder that science often works in ranges rather than absolute certainties. Implications for cosmology. Methuselah's age estimate, now safely within the age of the universe, has profound implications. It validates current cosmological models, reducing the tension that existed when initial age estimates seemed impossible. It provides a chronometer for the early universe, allowing astrophysicists to test theories of early star formation, cosmic expansion, and element creation. It helps refine our understanding of dark energy and cosmic expansion rates, since precise knowledge of early star ages informs models of how quickly the universe has expanded over billions of years. Summary of the clarification. A best current age estimate, 14.27 billion years. A universe age, 13.8 billion years. A margin of error, plus or minus 0.8 billion years. Interpretation. Methuselah is slightly younger than the universe, but close enough to be considered one of the first stars to form after the Big Bang. In essence, Methuselah has transformed from a cosmic paradox into a cornerstone of astrophysics, a tangible connection to the earliest moments of cosmic history. It allows astronomers to study conditions immediately following the Big Bang and provides a benchmark for refining stellar and cosmological models. In the context of Methuselah's age, the concept of margin of error is absolutely crucial for understanding why astronomers report its age as 14.27 plus or minus 0.8 billion years instead of a single, fixed number. Simply put, the margin of error quantifies the range within which the true age of the star is likely to fall, accounting for uncertainties in measurement, modeling, and interpretation. It's a statistical acknowledgement that, when dealing with events billions of years in the past, absolute precision is impossible. Why a margin of error exists for Methuselah? Several factors contribute to uncertainty in measuring the star's age. 1. Distance uncertainty. A stellar age is tightly linked to luminosity, which depends on how far away the star is. If the distance is underestimated, the star appears dimmer and thus older in stellar models. If overestimated, it appears brighter and younger. Even with precise instruments like the Hubble Space Telescope or the Gaia spacecraft, parallax measurements have small errors, which directly translate into age uncertainties. 2. Modeling stellar physics. The age is calculated using stellar evolution models that simulate how stars burn fuel, change in size, and emit light over time. These models rely on complex physics, including nuclear fusion rates, energy transport, element diffusion, and convection. Small uncertainties or assumptions in these models, like the exact rate of hydrogen fusion or how elements settle in the star's core, can shift the age estimate by hundreds of millions of years. 3. Metallicity measurements. A Methuselah has extremely low metallicity, meaning it formed when the universe had very few elements heavier than helium. Determining the exact metallicity from spectroscopic data is challenging, and minor errors in these measurements affect how quickly models predict the star should have evolved, and thus its calculated age. 4. Observational noise and instrument limitations. All telescopes and instruments have some degree of measurement noise, calibration uncertainty, or environmental interference. Over billions of years, even tiny observational errors can translate into substantial differences in inferred age. What plus or minus 0.8 billion years really means? The notation 14.27 plus or minus 0.8 billion years is a statistical way of saying, based on current observations and models, we are reasonably confident that Methuselah's true age lies somewhere between 13.47 billion and 15.07 billion years. This range reflects the combined effect of all sources of uncertainty: distance, luminosity, metallicity, and modeling assumptions. Crucially, this overlap with the universe's age, 13.8 billion years, means the star no longer appears paradoxically older than the cosmos. Why margins of error are important in astronomy? 1. They prevent overconfidence in measurements. Without reporting a margin of error, scientists might claim Methuselah is exactly 14.27 billion years old, which would be misleading. The error margin acknowledges the inherent uncertainty in working with astronomical distances and ancient objects. 2. They allow for meaningful comparisons. By including a range, astronomers can compare Methuselah's age with the universe's age and other stars without claiming impossibilities. For example, even though the central estimate is slightly older than 13.8 billion years, the error margin shows it is statistically consistent with being slightly younger, solving the age paradox. 3. They guide future observations. Knowing the margin of error helps scientists identify which measurements need refinement. For instance, if distance uncertainties dominate the error, Missions like Gaia or future JWST observations can focus on reducing that uncertainty. 4. They reflect the nature of science itself. A science rarely deals in absolutes. The margin of error is a recognition that our models and instruments, while incredibly advanced, cannot perfectly reconstruct events from billions of years ago. It's an honest acknowledgement of limits and confidence levels in our understanding. An analogy to make it clearer. Imagine trying to determine the age of an ancient tree by counting its rings, but some rings are faint, some are missing, and your ruler isn't perfectly calibrated. You might estimate it to be 1,000 years old plus or minus 50 years. The tree could be 950, 1,000, or 1,050 years old, but the central estimate gives your best guess. Similarly, Methuselah's plus or minus 0.8 billion year margin reflects the uncertainties inherent in studying such an ancient object. Key takeaway. The margin of error is not a flaw, it's a strength of scientific reporting. It acknowledges the complexity of estimating stellar ages billions of years after their formation and allows astronomers to present results that are both accurate and credible. In Methuselah's case, it resolves the initial paradox of a star older than the universe and positions the star as an astrophysical anchor for studying the early cosmos. Pinpointing the exact age of a star like Methuselah is a profound challenge, rooted in the sheer complexity of both the universe and the tools we use to study it. Even with decades of advances in astrophysics, spectroscopy, and space-based observations, astronomers cannot assign a precise, absolute number to a star's age because of multiple interdependent uncertainties that amplify over billions of years. Let's break down the key reasons why this is the case. 1. Limitations in observational data. Every measurement we make of a distant star is subject to instrumental limitations and environmental factors. A distance measurement uncertainty. Determining a star's distance is crucial for calculating its luminosity, which is a core factor in age estimation. A small error in parallax, the apparent shift in a star's position due to Earth's orbit, can significantly affect luminosity calculations. Luminosity, in turn, influences where the star falls on theoretical models of stellar evolution, affecting age estimates by hundreds of millions of years. A spectroscopic uncertainty. Age estimation requires precise knowledge of the star's chemical composition, particularly its metallicity. Spectroscopy can reveal elemental abundances, but the interpretation of spectral lines is influenced by temperature, pressure, and magnetic fields. Tiny measurement errors in spectral lines can lead to significant discrepancies in metallicity determination, cascading into age estimation errors. A brightness variability. Even slight variability in a star's brightness can influence its placement on the Hertzsprung-Russell diagram, HR diagram. Since stellar evolution models use HR diagram positions to infer age, small fluctuations in brightness measurements propagate to age uncertainty. 2. Dependence on stellar models. Stellar age is not measured directly. It's inferred from models of how stars evolve over time. These models involve complex physics that introduce multiple sources of uncertainty. A nuclear fusion rates, the rate at which a star fuses hydrogen into helium and heavier elements, determines its life cycle. Small errors in our understanding of nuclear reaction rates can shift age estimates substantially. Even a fraction of a% discrepancy in fusion rates can change the predicted main sequence lifetime of a star by hundreds of millions of years. A convection and energy transport. Stars transport energy from their cores to the surface through radiation and convection. Modeling these processes precisely, especially in low metallicity stars, like Methuselah, is extremely challenging. Slight variations in convection modeling can alter the star's predicted temperature, size, and luminosity over time, affecting the calculated age. Air element diffusion. Over billions of years, elements within the star slowly move and settle under gravity. This subtle process changes the star's internal composition, which impacts how it evolves. Stellar models must account for diffusion, but small uncertainties in diffusion rates affect age calculations. 3. Cosmic variability and early universe conditions. Methuselah is not just any star. It formed nearly 13 to 14 billion years ago, close to the Big Bang. The early universe was dramatically different from today. A primordial element ratios. In the early universe, the relative abundance of hydrogen, helium, and trace elements like lithium was different from what we see in most stars today. Even slight uncertainties in these primordial ratios affect theoretical models for how quickly Methuselah would have evolved. Influence of population 3 stars. Methuselah may have formed from the remnants of the first stars, population 3 stars. Because we have no surviving population 3 stars to observe, models rely on theoretical assumptions about their lifetimes, mass distributions, and explosion mechanisms. These assumptions introduce additional uncertainty in determining the ages of second-generation stars like Methuselah. 4. Measurement precision limits. Even our most advanced instruments have inherent limitations. Hubble and Gaia observations. While the Hubble Space Telescope and Gaia mission provide unparalleled parallax and luminosity data, no instrument is perfect. Measurement noise, calibration uncertainties, and minor systematics mean that all derived quantities, distance, luminosity, metallicity, carry a small but significant error margin. Interstellar effects. Light from Methuselah travels through interstellar space for approximately 190 light-years. Dust and gas can slightly dim or redden the light, affecting observed properties. Although astronomers correct for this, minor inaccuracies remain. 5. Compounding effects over time. When estimating the age of a star billions of years old, even tiny uncertainties in each variable, distance, metallicity, fusion rate, convection modeling, compound. Unlike short-term measurements in a lab, errors over cosmic timescales multiply in ways that make pinpointing a single exact age impossible. To illustrate, a 1% error in distance measurement might cause a 0.5 to 1 billion year uncertainty in age. A 1 to 2% uncertainty in metallicity or fusion rates may add hundreds of millions of years of uncertainty. When combined with other observational and modeling errors, the total uncertainty reaches the plus or minus 0.8 billion year margin of error we see for Methuselah. 6. Philosophical aspect of stellar age. Finally, there is a subtle, almost philosophical reason why an exact age cannot be assigned. Stars are not clocks in the absolute sense. Unlike a ticking clock, a star's evolution depends on numerous interrelated variables. The star does not record its age in a single, measurable quantity. Astronomers must infer it indirectly through models and observations. This means that any reported age is inherently a best estimate with associated uncertainty. Summary. In short, scientists cannot pin down Methuselah's exact age because 1. Observational data have intrinsic limitations and noise. 2. Stellar models involve complex physics with unavoidable assumptions. 3. Early universe conditions introduce additional uncertainty. 4. Even the most advanced instruments cannot measure all required variables perfectly. 5. Errors in multiple factors compound over billions of years. Thus, the age of 14.27 billion years comes with a margin of error of plus or minus 0.8 billion years, representing the limits of both current observational precision and theoretical modeling. Despite these uncertainties, Methuselah remains one of the oldest known stars and a critical tool for understanding the early universe. The idea that Methuselah might have formed shortly after the Big Bang is one of the most fascinating aspects of this star, linking it directly to the earliest chapters of cosmic history. When we say Methuselah is almost as old as time itself, we are referring to the fact that this star could have originated within the first few 100 million years after the universe's birth, at a time when the cosmos was an extremely different place than it is today. The universe's early timeline. To contextualize Methuselah's potential formation period, we need to revisit the timeline of the early universe. 1. Big Bang, 13.8 billion years ago. The universe began as an extremely hot, dense point, expanding and cooling rapidly. During this epoch, only the simplest elements, hydrogen, helium, and traces of lithium, existed. 2. Recombination, 380,000 years after the Big Bang. The universe cooled enough for electrons to combine with nuclei, forming neutral atoms. Light could finally travel freely, creating the cosmic microwave background radiation, CMB, that we detect today. 3. Cosmic Dark Ages, 380,000 to 150 million years after the Big Bang. During this period, there were no stars or galaxies, just vast clouds of neutral hydrogen and helium. It was a dark and quiet era in cosmic history. 4. Formation of the first stars, population 3 stars, tilde 150–400 million years after the Big Bang. These primordial stars were massive, short-lived, and composed almost entirely of hydrogen and helium. Their explosive deaths seeded the universe with heavier elements. It is within this cosmic dawn, shortly after the first generation of stars enriched the interstellar medium, that Methuselah likely formed. This would make it one of the very first stars to exist in a universe that had barely begun to structure itself into galaxies. Methuselah's formation conditions. Several factors point to Methuselah's extremely early formation. 1. Low metallicity. A metallicity refers to the proportion of elements heavier than helium. Methuselah's metallicity is extraordinarily low, indicating it formed before successive generations of stars had time to significantly enrich the universe. This suggests Methuselah is a second-generation star, possibly a direct descendant of population 3 stars. 2. Location in the galactic halo. A Methuselah resides in the galactic halo, a roughly spherical region surrounding the Milky Way's disk. Stars in the halo are generally older and less chemically enriched than those in the disk, supporting the idea that Methuselah formed in the early universe. 3. Longevity of low-mass stars. A massive early stars burned out quickly, but smaller stars like Methuselah, with lower masses, can burn their fuel very slowly. This allows them to survive for over 13 billion years, meaning they could persist from the cosmic dawn to the present. Implications of early formation. Understanding that Methuselah formed shortly after the Big Bang has profound implications. 1. A living fossil of the early universe. A Methuselah serves as a stellar time capsule, preserving chemical signatures from an era before most stars and galaxies formed. By studying its composition, astronomers can infer the processes that shaped the first generation of stars and the early universe. 2. Clues about population 3 stars. A direct observation of population 3 stars is currently impossible because they were massive and short-lived. Methuselah offers an indirect window into their existence, as it likely formed from material enriched by these primordial stars. 3. Testing cosmological models. Knowing Methuselah's age helps constrain models of cosmic expansion, galaxy formation, and dark energy, since its formation must fit within the timeline set by the Big Bang and subsequent cosmic evolution. How soon after the Big Bang? While we cannot pinpoint the exact year Methuselah formed, models suggest the first population 3 stars may have formed around 150 to 200 million years after the Big Bang. Methuselah, as a second-generation star, likely formed a few tens of millions of years later, perhaps around 200 to 400 million years post-Big Bang. This means that, in a cosmic sense, Methuselah has witnessed nearly the entire history of the universe, from the emergence of the first stars and galaxies to the modern cosmos we observe today. A cosmic perspective. To put it in human terms, if the universe's history were compressed into a single year, Methuselah would have formed within the first few days after the Big Bang. Everything we see in the night sky today, galaxies, nebulae, planets, and even life on Earth, was built upon the foundations laid during the time of Methuselah's formation. This perspective underscores why Methuselah captivates astronomers and the public alike. It is a direct link to the universe's infancy, an ancient witness to cosmic evolution that has persisted for nearly the entire span of existence itself. Key takeaway. Methuselah is not merely an old star, it is a relic of the universe's earliest epochs, likely formed shortly after the Big Bang and just after the first generation of stars transformed the cosmos. Its age and composition provide a unique lens through which scientists can study the dawn of stellar formation, the enrichment of elements, and the early assembly of galaxies. In essence, Methuselah allows us to peer back into a time when the universe itself was still young, chaotic, and full of possibilities. One of the most compelling aspects of Methuselah's origin is the theory that it formed from the remnants of the universe's very first stars, known as population 3 stars. These stars were unlike anything we see today. They were massive, short-lived, and made almost entirely of hydrogen and helium, with virtually no metals, elements heavier than helium. Understanding the link between Methuselah and population 3 stars gives us a window into the very first chapter of cosmic history. Who were the population 3 stars? To appreciate Methuselah's connection, we first need to understand what makes population 3 stars special. 1. The first stars. A population 3 stars were the universe's first generation of stars, forming roughly 150 to 400 million years after the Big Bang. Since the early universe contained only hydrogen, helium, and trace amounts of lithium, these stars had almost no metals. This low metallicity profoundly affected their structure, luminosity, and evolution. 2. Massive and short-lived. Theoretical models suggest many population 3 stars were hundreds of times the mass of the Sun, meaning they burned their nuclear fuel extremely quickly, lasting only a few million years. By contrast, stars like Methuselah burn much more slowly and can survive for over 13 billion years. 3. Cosmic alchemists. Despite their brief existence, population 3 stars were responsible for creating the first heavy elements through nuclear fusion and supernova explosions. These elements, carbon, oxygen, iron, and others, seeded the universe and allowed later generations of stars to form with higher metallicity. Methuselah as a second-generation star. Methuselah is believed to belong to the second generation of stars, sometimes called population 2 stars. The theory goes like this. 1. Birth from enriched gas clouds. When a population 3 star exploded as a supernova, it released heavy elements into the surrounding gas. A Methuselah likely formed from a gas cloud enriched by the debris of these early stars. Its extremely low metallicity indicates that it formed very early in the sequence of stellar generations, before metals became abundant. 2. Chemical fingerprints. Astronomers analyze Methuselah's chemical composition to identify signatures of population 3 enrichment. Its elemental ratios, particularly the scarcity of iron and abundance of certain light elements, suggest it inherited material processed by these primordial stars, confirming its status as a near-direct descendant. 3. Survivor of cosmic history. While most massive population 3 stars vanished billions of years ago, Methuselah survived because it is low mass. Its long lifespan preserves a record of the conditions that existed in the early universe. Why population 3 remnants are important. Studying stars like Methuselah gives us insight into the first generation of stars, which we cannot observe directly. 1. Testing stellar evolution models. Because population 3 stars are extinct, astronomers rely on second-generation stars to test theories about how the earliest stars formed, evolved, and exploded. Methuselah serves as a living laboratory for validating these models. 2. Understanding galactic formation. A population 3 supernovae influenced the formation of the first galaxies. By examining Methuselah, we can infer how these early explosions enriched the interstellar medium and shaped the Milky Way's halo, where Methuselah now resides. 3. Clues about the universe's first elements. A Methuselah contains clues about the ratios of elements that existed immediately after the first stars died. This helps cosmologists reconstruct the timeline of chemical evolution in the universe. Theoretical and observational evidence. 1. Computer simulations. Cosmologists simulate the early universe to predict where population 3 stars formed and how they enriched the gas. These simulations suggest that stars like Methuselah are plausible direct descendants of population 3 remnants. 2. Metallicity comparisons. Methuselah's metallicity is exceptionally low compared to typical population 2 stars, consistent with formation from nearly pristine gas enriched by just one or a few population 3 supernovae. 3. Stellar kinematics. Its motion in the galactic halo supports the idea that it originated in a primordial environment rather than the galactic disk, further linking it to early cosmic history. Implications of the population 3 connection. 1. Cosmic archaeology. Methuselah acts as a fossil record of the first stars, allowing astronomers to study an era of the universe that would otherwise remain inaccessible. 2. Refining cosmological models. By understanding the timing and chemical output of population 3 stars through Methuselah, scientists can fine-tune models of galaxy formation, the enrichment of elements, and the behavior of early cosmic structures. 3. Perspective on cosmic lifespans. While population 3 stars lived for only a few million years, Methuselah has survived for over 13 billion years. This contrast underscores the diversity of stellar lifespans and the rarity of such ancient stars still observable today. Key takeaway. Methuselah is not just an ancient star, it is a bridge between the universe's first stars and everything that followed. By forming from the remnants of population 3 stars, Methuselah preserves a direct connection to the universe's formative moments, carrying chemical and physical evidence from a time long before our Sun, or even our galaxy, existed. Its existence allows astronomers to peer into the past, shedding light on the earliest stellar generations and the initial steps of cosmic evolution. Studying Methuselah provides more than just a glimpse into the universe's distant past. It also plays a crucial role in refining cosmological models, the framework scientists use to understand the origin, evolution, and large-scale structure of the universe. This star, nearly as old as the universe itself, acts as a benchmark for validating theories about cosmic history, from the Big Bang to the expansion of galaxies and the behavior of dark energy. Methuselah as a cosmic chronometer. One of the most important contributions of Methuselah to cosmology is its role as a cosmic chronometer, essentially a natural clock for measuring the age of the universe. 1. Age constraints on the universe. A Methuselah's estimated age of about 14.27 billion years, slightly younger than the 13.8 billion year age of the universe, provides a critical check on cosmological models. If Methuselah appeared older than the universe, as early measurements suggested, it would signal a fundamental problem in our understanding of cosmic expansion, the Big Bang timeline, or stellar physics. 2. Benchmarking stellar evolution models. To accurately estimate a star's age, astronomers rely on models of how stars evolve, including fusion rates, luminosity changes, and chemical composition over time. A Methuselah's extreme age challenges these models to remain consistent with observed data, refining our understanding of stellar physics and population synthesis in the early universe. 3. Cross-checking cosmic timelines. Cosmologists calculate the universe's age using multiple methods: cosmic microwave background, CMB, measurements, galaxy distributions, supernovae distances, and globular cluster ages. A Methuselah's age serves as an independent verification of these models, ensuring that the timeline of cosmic history aligns across different observational techniques. Testing theories of cosmic expansion. Methuselah's age also provides insights into the expansion history of the universe, a key aspect of modern cosmology. 1. Hubble constant calibration. The Hubble constant, h, measures the rate at which the universe expands. Different methods sometimes yield slightly different values, a discrepancy known as the Hubble tension. By establishing that ancient stars like Methuselah formed shortly after the Big Bang, scientists can cross-check expansion rates and timelines, helping to refine the Hubble constant and resolve inconsistencies. 2. Constraints on dark energy. A dark energy is the mysterious force driving the universe's accelerated expansion. Methuselah's age indirectly constrains dark energy models. If stars existed too early or too late relative to cosmic expansion models, it would indicate a miscalculation in dark energy's influence over time. 3. Cosmic chronology verification. A Methuselah helps verify the sequence of cosmic events: formation of the first stars, reionization, galaxy formation, and large-scale structure development. If its age were inconsistent with cosmological predictions, it would force scientists to rethink the timeline of the universe's evolution. Chemical clues for cosmological models. Methuselah also provides chemical evidence crucial for refining models of cosmic evolution. 1. Metallicity as a cosmic probe. The star's extremely low metallicity indicates that it formed from gas only lightly enriched by previous stellar generations, supporting theories about how and when the first stars enriched the interstellar medium. Models of galaxy formation and chemical evolution can be adjusted based on Methuselah's elemental composition, improving the accuracy of simulations that track how stars and galaxies developed over billions of years. 2. Tracing early supernova activity. By examining the ratios of certain elements in Methuselah, astronomers can infer the types of supernovae that occurred in the early universe and the speed at which heavy elements spread through interstellar space. These chemical fingerprints provide key inputs for cosmological models, linking stellar evolution with galaxy evolution and large-scale structure formation. Testing theories of the first stars and galaxies. Methuselah's origin and composition also help refine models of the first stars and galaxies. 1. Population 2-star formation. Methuselah, as a likely second-generation star, demonstrates how the first population 3 stars influenced subsequent generations. Cosmologists use these data to improve simulations of early star formation rates, helping predict how many early galaxies formed and how quickly they evolved. 2. Early galactic halo formation. A Methuselah resides in the Milky Way's halo, a region that formed from the merging of smaller protogalaxies. Studying its motion and chemical composition allows scientists to reconstruct the Milky Way's formation history, testing models of hierarchical galaxy assembly. 3. Validation of cosmic reionization models. The timing of Methuselah's formation aligns with the era of cosmic reionization, when the first stars ionized neutral hydrogen and made the universe transparent to light. Its existence provides constraints on the models of reionization, helping scientists determine when and how quickly this process occurred. Reducing uncertainty in cosmology. Methuselah's unique properties help reduce uncertainties in several cosmological parameters. 1. Narrowing stellar age ranges. By comparing Methuselah with other ancient stars, astronomers refine the distribution of stellar ages in the galaxy. This helps constrain models of star formation rates, chemical enrichment timelines, and the overall age distribution of the galactic halo. 2. Consistency checks across observations. Methuselah serves as a touchstone for multiple datasets, Hubble observations, spectroscopic analyses, and Gaia measurements of parallax and motion. Cross-checking these independent observations against cosmological predictions ensures the robustness of current models. 3. Benchmark for future observations. As telescopes like the James Webb Space Telescope, JWST, study ancient stars and galaxies in greater detail, Methuselah provides a local calibration point for interpreting distant, early universe objects. Key takeaway. Methuselah is far more than an exceptionally old star. It is a cornerstone for understanding the universe itself. Its age, chemical composition, and position provide vital data that refine cosmological models, test the accuracy of expansion rates, illuminate the processes that shape the first galaxies, and constrain theories about dark energy. By studying Methuselah, scientists can anchor the history of the cosmos to a tangible, observable point, turning abstract models into a reality tied to a star that has been shining since nearly the dawn of time. The Methuselah Star isn't just remarkable for its extreme age, it also provides a unique window into the behavior of the universe itself, particularly when it comes to dark energy and cosmic expansion. Understanding this link requires us to examine how the timing of the universe's earliest stars interacts with models of the universe's growth and acceleration. Cosmic expansion and the universe's timeline. The concept of cosmic expansion originates from Edwin Hubble's observations in the 1920s that galaxies are moving away from us, with their speeds proportional to their distances. This discovery laid the foundation for the Big Bang theory. The universe began in a hot, dense state and has been expanding ever since. 1. The Hubble constant, h. The Hubble constant measures the rate at which the universe expands. Current estimates, primarily from observations of the cosmic microwave background, CMB, and Type Ia supernovae, yield slightly different results, a discrepancy known as the Hubble tension. Stars like Methuselah provide an independent check on the expansion timeline. If Methuselah is almost as old as the universe, it constrains how quickly the universe must have expanded to reach its current state without conflicting with observed stellar ages. 2. Age of the universe. Cosmologists use several methods to calculate the universe's age. The age derived from CMB measurements by the Planck satellite is about 13.8 billion years, while the initial Methuselah age estimate was 16 billion years, suggesting a potential conflict. Resolving this required refinements in both stellar modeling and distance measurements. The revised age of Methuselah, approximately 14.27 billion years, is slightly older than the universe's age estimate but within the margin of error, making it compatible with cosmological models. Dark energy and accelerated expansion. In 1998, astronomers discovered that the universe's expansion is accelerating, driven by a mysterious force called dark energy. Methuselah provides a subtle but critical test of theories involving dark energy. 1. Constraints on cosmic history. A dark energy influences how fast the universe expands over time. If stars like Methuselah formed very early, the expansion rate must allow for their formation within the timeline of the universe. Essentially, Methuselah's age sets a minimum age for the universe at the time of its birth, which in turn constrains the energy density of dark energy needed to produce the observed acceleration. 2. Indirect evidence of cosmic acceleration. By knowing when Methuselah formed, astronomers can infer how long the universe had been expanding at various rates before stars could coalesce from primordial gas clouds. If dark energy was stronger or weaker in the past, the timing of star formation would shift. Methuselah's existence helps rule out certain extreme models of dark energy evolution. 3. Calibration of cosmological models. Cosmological simulations often involve input parameters like dark energy density, matter density, and the Hubble constant. Methuselah serves as a real-world anchor, ensuring that these models produce a universe where ancient stars can form in a timeline consistent with their observed ages. Methuselah and the expansion timeline. Understanding the link between Methuselah and cosmic expansion requires thinking about the sequence of events in the early universe. 1. Post-Big Bang conditions. After the Big Bang, the universe was hot, dense, and dominated by radiation. Over time, it cooled, allowing hydrogen and helium to combine and eventually form the first stars. Methuselah's formation shortly after this epoch provides evidence that the universe's expansion had slowed sufficiently to allow gas clouds to collapse into stars. 2. Epoch of reionization. Methuselah formed during or just after the epoch of reionization, when the first stars ionized neutral hydrogen, making the universe transparent to light. By confirming the age and timing of Methuselah, astronomers can better model the pace of early cosmic expansion and the role of energy sources in heating and ionizing the interstellar medium. 3. Expansion rate and star formation. The universe must expand at a rate that balances the gravitational collapse of gas clouds into stars. If expansion were too rapid, primordial gas would disperse before stars could form. Too slow, and early star formation would occur earlier than observed. Methuselah serves as a critical data point, ensuring that theoretical expansion rates match the observed existence of the oldest stars. Testing dark energy theories with ancient stars. Methuselah also helps in evaluating dynamic dark energy models, which suggest that the energy driving cosmic acceleration might vary over time. 1. Constant versus variable dark energy. If dark energy density was significantly different in the early universe, stars like Methuselah might not have been able to form at the times we observe. Methuselah's age supports models where dark energy was relatively weak in the early universe, allowing matter to collapse into stars, and stronger later, driving the accelerated expansion observed today. 2. Fine-tuning of cosmological parameters. Cosmologists adjust parameters like the cosmic matter density, dark energy equation of state, and curvature of space to match observational constraints. Methuselah provides a constraint on these parameters, because any model must produce a universe old enough to contain this star while still consistent with the observed cosmic expansion. Implications for our understanding of the universe. 1. Bridging micro and macro. Methuselah connects the micro-level physics of stellar evolution with macro-level cosmology. By examining the nuclear processes within the star, we can test large-scale models of the universe's growth. 2. Consistency check across observations. Ancient stars like Methuselah complement other cosmological measurements, such as Type Ia supernova distances, galaxy surveys, and the CMB. This cross-validation ensures that the story of cosmic expansion is coherent across multiple datasets. 3. Anchor for future theories. As telescopes probe ever further into the universe's infancy, stars like Methuselah act as a local benchmark to test whether distant observations of early galaxies, quasars, and supernovae align with the predicted cosmic expansion. Key takeaway. Methuselah is far more than a relic of the early universe. It is a cosmic timekeeper, offering critical insights into dark energy and the expansion history of the cosmos. Its age constrains the minimum time required for star formation, calibrates models of the Hubble constant, and provides indirect evidence for the evolution of dark energy. In essence, by studying this single ancient star, astronomers can test and refine the very framework that describes how the universe grows and evolves over billions of years. Over the years, the Methuselah Star has not only captured the attention of mainstream astronomers but also become the subject of various alternative or fringe theories, many of which stretch conventional physics or cosmology to their limits. While these ideas are intriguing in popular media, they generally lack robust observational evidence or theoretical plausibility, which is why the scientific community largely dismisses them. Exploring these fringe perspectives helps illustrate the rigor of mainstream science and why it relies on careful measurements and validated models. 1. Age paradox theories. Stars older than the universe. One of the earliest sparks for fringe discussion came from the initial age estimates of Methuselah, which suggested it might be 16 billion years old, apparently older than the universe itself. Some speculative thinkers proposed time anomalies or local time dilation. The idea here is that Methuselah somehow experienced a different rate of time, making it appear older to observers on Earth. Why mainstream science rejects it. While general relativity allows time dilation in strong gravitational fields or at near-light speeds, Methuselah resides in the Milky Way's halo with no extraordinary gravitational or velocity conditions that could create a time discrepancy of billions of years. The effect simply cannot account for such extreme differences. Alternative cosmologies. Some suggested that the universe might be older than the 13.8 billion years derived from the cosmic microwave background, CMB, data, potentially resolving the age paradox. Why mainstream science rejects it. These models often conflict with multiple independent datasets, including CMB measurements, galaxy distributions, supernovae observations, and nucleosynthesis models. The evidence overwhelmingly supports a 13.8 billion year universe, and refining stellar age estimates, rather than rewriting cosmology, resolves the apparent conflict. 2. Alien or artificial origins. A more imaginative fringe hypothesis claims that Methuselah's unusual properties could indicate artificial manipulation or even extraterrestrial engineering. Are arguments made by proponents. They point to Methuselah's low metallicity and extreme age as evidence that it doesn't fit normal stellar evolution patterns. A scientific response. The star's properties are entirely consistent with population 2 stars formed shortly after the first stars, population 3. Low metallicity is expected in such ancient stars, and no known observational data suggest artificial intervention. Mainstream astrophysics has robust models explaining its composition and age without invoking exotic explanations. 3. Modified physics or exotic matter hypotheses. A few speculative ideas suggest that stars like Methuselah might contain exotic matter or operate under unknown physics that drastically slows aging. Concepts proposed. Stars could have unknown mechanisms that extend their lifespans far beyond standard stellar models. Nuclear reactions in such stars might proceed at anomalously slow rates, creating the illusion of extreme age. Why these ideas aren't accepted. Detailed spectroscopic and photometric studies of Methuselah match standard population 2 star models, including predicted nuclear fusion pathways. No anomalies in light emission, elemental composition, or stellar structure suggest the presence of unknown physics. Occam's razor favors the simpler explanation. Methuselah is a very old, but entirely ordinary star, within the expected physical framework. 4. Mainstream science's approach to extraordinary claims. Science maintains rigor and skepticism, especially when dealing with claims that contradict well-established principles. 1. Reliance on multiple observations. Methuselah's age isn't derived from a single measurement. Researchers use parallax data, luminosity, spectral analysis, and stellar evolution models. When new data, like refined Hubble or Gaia measurements, are incorporated, the age estimates adjust in ways consistent with known physics, not fringe speculations. 2. Peer review and reproducibility. Alternative theories often fail to meet peer review standards or cannot be independently reproduced. Methuselah's mainstream age estimates have been confirmed by multiple independent teams, solidifying confidence in the results. 3. Compatibility with broader cosmology. Any valid theory must fit with the broader universe, including the Big Bang, cosmic microwave background, nucleosynthesis, and galaxy formation models. Fringe claims rarely survive this comprehensive scrutiny. Methuselah fits neatly into the timeline of stellar and cosmic evolution once measurement errors are accounted for. Key takeaway. While it is tempting to imagine stars older than the universe, alien-engineered celestial objects, or miraculous time anomalies, Methuselah's observed properties are fully explained by established astrophysical principles. Its low metallicity, age, and location in the galactic halo make it a perfect exemplar of an ancient population 2 star, formed shortly after the first generation of stars. Mainstream science embraces extraordinary discovery, but only when it passes the test of empirical evidence, reproducibility, and theoretical consistency, criteria that most fringe theories fail to meet. In short, Methuselah is remarkable without needing to invoke the extraordinary. The real science is compelling enough on its own, and its story is a triumph of careful measurement, modeling, and patience. To truly grasp the astonishing age of the Methuselah Star, it helps to place it in context with our own Sun, a star whose life cycle we understand intimately because of its proximity and the wealth of observational data available. While the Sun is often thought of as a typical star, Methuselah represents a vastly different chapter in the cosmic timeline, a relic from a much earlier epoch in the universe's history. The Sun, a middle-aged star. Our Sun is about 4.6 billion years old, having formed roughly 9.2 billion years after the Big Bang. In stellar terms, it is a population 1 star, meaning it formed in a later generation with a higher metallicity due to the enrichment of the interstellar medium by previous generations of stars. The Sun has enough hydrogen fuel to continue fusing in its core for another 5 billion years or so, after which it will expand into a red giant before shedding its outer layers and leaving behind a white dwarf. Its life cycle, energy output, and composition have been extensively studied, giving astronomers a benchmark for modeling stellar evolution. In short, the Sun is relatively young compared to Methuselah and represents a mature but not ancient example of star formation in the universe. Methuselah, a star from the universe's dawn. Methuselah, in stark contrast, is estimated to be about 14.27 billion years old, placing its formation within the first billion years after the Big Bang. Comparing this to the Sun reveals a staggering disparity. 1. Age ratio. A Methuselah is over 3 times older than the Sun, meaning it formed during an era when the universe was vastly different, much less chemically enriched, with primarily hydrogen and helium, and virtually no heavy elements like iron or carbon. While the Sun benefited from the recycling of material from earlier generations of stars, Methuselah likely formed from nearly pristine primordial gas. 2. Galactic context. The Sun resides in the galactic disk, an area rich with metals, star clusters, and ongoing star formation. Methuselah, by contrast, is in the galactic halo, a sparsely populated region filled with ancient stars orbiting the Milky Way center in extended, elliptical paths. This difference highlights not just the age disparity but also the evolution of the Milky Way over billions of years. 3. Metallicity and composition. The Sun has a relatively high metallicity, which contributes to the formation of planets, moons, and complex chemistry. Methuselah's extremely low metallicity points to a time before most stars had created the heavier elements that populate later stellar generations. This difference emphasizes that Methuselah predates the formation of planetary systems like ours. In essence, while the Sun could host life-supporting planets billions of years after Methuselah's birth, Methuselah emerged in a cosmos too young for planets as we know them. Implications of the age comparison. 1. Perspective on cosmic time. The Sun's 4.6 billion years might seem ancient in human terms, but it's a youthful moment in the universe's history compared to Methuselah. The Methuselah Star has existed through more than 3 times the Sun's current lifetime, witnessing nearly the entire history of cosmic evolution, including the formation of galaxies, supernovae, and planetary systems. 2. Insight into stellar generations. The comparison illustrates the generational cycle of stars. Methuselah represents population 2, some of the earliest stars to form, while the Sun is population 1, enriched by the remnants of stars like Methuselah. Every star like the Sun owes its chemical richness to the ancient stars that came before, underlining the crucial role of early stars in shaping the universe. 3. Perspective on life and planet formation. Planetary systems, and by extension life as we understand it, require elements heavier than helium. Methuselah predates significant metal enrichment, implying that it formed in a universe not yet capable of producing planets like Earth. By the time the Sun formed, enough generations of stars had already seeded the cosmos with metals, enabling the creation of rocky planets, oceans, and eventually life. Visualizing the timeline. Imagine a cosmic clock where, at 0 billion years, Big Bang occurs. At 0.11 billion years, Methuselah forms, a near-primordial star. 4.6 billion years ago, Sun forms in a chemically enriched galaxy. At present day, both stars continue shining, but the Methuselah Star has been a silent witness to almost the entire history of the universe, while the Sun is just at the midpoint of its life cycle. This perspective emphasizes the rarity and significance of Methuselah. It isn't just an old star, it is an ancient survivor, providing a living record of the cosmos long before the solar system existed. Key takeaways. A Methuselah is over 3 times older than the Sun, placing it among the oldest stars known. The Sun, though middle-aged and chemically rich, formed well after early stars like Methuselah had already lived through the universe's formative events. Comparing these two stars highlights the vastness of cosmic time, illustrating how early stars seeded the universe for future generations like our Sun. Methuselah's enduring presence allows astronomers to study the universe as it existed shortly after the Big Bang, a feat impossible with younger stars like the Sun. By contrasting Methuselah and the Sun, we gain not just a sense of scale but also a deep appreciation for the continuity of cosmic history, from the first glimmers of starlight to the rich, life-supporting cosmos that emerged billions of years later. Stars like Methuselah are not just old, they are extraordinarily rare, especially in the region of the Milky Way near our Sun. Understanding their rarity helps highlight why discovering such ancient stars is a milestone in observational astronomy, providing a glimpse into the early universe that few other objects can offer. 1. Population 2 stars and their scarcity. Methuselah belongs to a class of stars known as population 2 stars. Population 1 stars, like the Sun, are younger, metal-rich stars found primarily in the galactic disk. They dominate the stellar population in our neighborhood. Population 2 stars, on the other hand, are metal-poor, ancient stars that formed in the first billion years after the Big Bang. They are mostly found in the galactic halo and in globular clusters, orbiting the Milky Way in wide, often elliptical trajectories. Population 3 stars, theorized to be the very first generation, were nearly pure hydrogen and helium, but none have been observed directly. They likely all exploded or evolved long ago. Methuselah, therefore, is a rare survivor of an early population, existing at the periphery of the galaxy while most other ancient stars have long since evolved or merged into other stellar remnants. 2. Sparse distribution in the galactic halo. Methuselah resides in the halo of the Milky Way, a vast, roughly spherical region surrounding the galactic disk. Stars in the halo are few and far between, unlike the dense, star-rich disk. Most stars in our local neighborhood are younger, metal-rich population 1 stars, making Methuselah a striking outlier. The halo contains ancient stars orbiting in eccentric paths, some traveling hundreds or thousands of light-years above and below the galactic plane. Methuselah is part of this scattered ancient population. The sparse distribution of halo stars explains why Methuselah-like stars are so rarely observed near the Sun. Astronomers must search through large volumes of space and use precise measurements to identify them. 3. Identification challenges. Finding stars like Methuselah is challenging because 1. Distance and faintness. Halo stars are often much farther away than nearby disk stars. Methuselah's relative proximity, 190 light-years, is unusual. Most similar stars are much more distant, making them fainter and harder to study. 2. Low metallicity makes detection harder. Many surveys target brighter, metal-rich stars. Low metallicity stars like Methuselah have subtle spectral features, requiring high-resolution spectroscopy to identify. 3. Rarity combined with halo dynamics. Because halo stars often have fast, elliptical orbits, they spend only part of their time near the Sun, further reducing the likelihood of detection. 4. Methuselah as a living fossil. Astronomers often describe stars like Methuselah as living fossils of the galaxy. They are ancient remnants that have survived for almost the entire history of the universe. Unlike most stars that have ended their life cycles, these stars are still shining and providing critical information about the conditions of the early cosmos. Observing them allows scientists to trace the chemical evolution of the galaxy, because their low metallicity reflects the composition of the universe shortly after the first generation of stars produced heavier elements. Methuselah's survival is rare and remarkable, offering a direct link to the universe's formative years. 5. Statistical perspective. To understand just how rare Methuselah is, the Milky Way contains roughly 100 to 400 billion stars. The majority of stars are population 1. Population 2 stars make up a small fraction, mostly located in the halo or globular clusters. Among population 2 stars, extremely low metallicity stars like Methuselah are exceedingly uncommon. Some estimates suggest only a few % of halo stars are as metal poor. In essence, Methuselah is a cosmic needle in a haystack, not only ancient but also a survivor with properties that allow it to be studied in unprecedented detail. 6. Implications of its rarity. The scarcity of Methuselah-like stars has significant scientific implications. 1. Windows into the early universe. Each star acts as a time capsule, preserving information about the universe's composition and structure shortly after the Big Bang. 2. Calibration of cosmological models. Rare stars help test theories of galaxy formation, chemical enrichment, and stellar evolution. Without them, many models would lack direct observational benchmarks. 3. Inspiration for future surveys. Methuselah motivates astronomers to use large-scale sky surveys and next-generation telescopes to uncover more ancient stars, further refining our understanding of cosmic history. 7. Why its neighborhood status is remarkable. Methuselah's relative closeness to the Sun, just about 190 light-years away, is unusual. Most stars of comparable age and metallicity are hundreds or thousands of light-years away, making detailed studies difficult. Its proximity allows astronomers to measure parallax accurately, analyze its spectrum in detail, and obtain more precise age estimates than would be possible for more distant ancient stars. In other words, not only is Methuselah rare, but it's also exceptionally well positioned. 4. Scientific observation, a cosmic stroke of luck for humanity's understanding of the early universe. Key takeaways. Stars like Methuselah are extremely rare in our galactic neighborhood. Its low metallicity and ancient age place it among the earliest survivors of the universe, likely formed shortly after the first generation of stars. Its presence in the halo and relative proximity to the Sun make it a living fossil, providing unparalleled insights into the primordial universe. Studying rare stars like Methuselah allows astronomers to reconstruct the chemical and dynamic evolution of the Milky Way. The extreme rarity of Methuselah emphasizes its value, not just as a scientific object, but as a cosmic witness to the universe's earliest chapters, a survivor of an era most stars have long left behind. Finding a star like Methuselah is nothing short of discovering a living fossil in the vast expanse of the cosmos. Just as paleontologists treasure ancient fossils for the glimpse they provide into life millions of years ago, astronomers prize stars like Methuselah for their ability to reveal the conditions and processes of the early universe. This analogy isn't merely poetic, it reflects the scientific and historical significance of these rare stellar relics. 1. What makes Methuselah a living fossil? Several characteristics of Methuselah contribute to this designation. 1. Extreme age. With an age estimate around 14.27 billion years, Methuselah formed almost immediately after the universe itself came into existence. Unlike most stars that have long since expired or evolved into white dwarfs, supernova remnants, or neutron stars, Methuselah has persisted through virtually the entire history of the cosmos. 2. Primitive composition. Methuselah has extremely low metallicity, meaning it contains only trace amounts of elements heavier than helium. This composition mirrors the early universe's makeup, giving scientists a direct window into the chemical environment of first-generation star formation, long before subsequent stellar generations enriched the cosmos with heavier elements. 3. Isolation in the galactic halo. Unlike stars in the crowded disk of the Milky Way, Methuselah resides in the sparse halo, where fewer gravitational interactions and stellar collisions occur. This isolation has contributed to its remarkable preservation, much like how fossils in undisturbed sedimentary layers survive for millions of years. 2. Why astronomers compare it to fossils. The fossil analogy works on multiple levels. 1. Time capsule. Fossils preserve evidence of life as it existed eons ago. Methuselah preserves evidence of the stellar and chemical conditions of the early universe. Its elemental composition acts as a snapshot of the primordial gas clouds from which it formed. 2. Rare survivors. Just as fossils are remnants of countless organisms that have mostly decomposed or eroded away, stars like Methuselah are the few remaining survivors of the earliest stellar populations. 3. Clues to evolution. Paleontologists study fossils to reconstruct evolutionary history. Similarly, astronomers study Methuselah to trace the evolution of galaxies, chemical enrichment, and star formation over cosmic time. 4. Scientific value. Fossils provide data that cannot be recreated or observed directly. Methuselah offers unique insight into a period of the universe that cannot be observed today because most other stars from that epoch no longer exist. 3. Methuselah as a benchmark for ancient stars. Methuselah is more than a curiosity. It is a reference point for ancient stellar populations. Its age and metallicity serve as a benchmark for identifying other population II stars. By comparing Methuselah with similar stars, astronomers can reconstruct a timeline of star formation in the early universe. It also allows scientists to test and refine models of stellar evolution, particularly for low metallicity stars, whose lifetimes and fusion processes differ from younger, metal-rich stars like the Sun. 4. Preservation over cosmic time. Several factors contributed to Methuselah's survival, reinforcing the living fossil analogy. 1. Low mass. A Methuselah has a mass slightly less than the Sun, meaning its fusion rate is slower, allowing it to live much longer than more massive, short-lived stars. 2. Halo orbit. By orbiting the Milky Way's halo, Methuselah avoids dense regions where gravitational interactions could disrupt or eject stars. 3. Stable internal processes. Its internal fusion reactions have remained stable for billions of years, allowing it to endure while more volatile. Massive stars from the same era have already ended their lifespans. 5. Learning from a cosmic fossil. Studying Methuselah provides insight that is impossible to obtain from younger stars. Chemical clues. Its low metallicity informs scientists about the primordial abundances of elements shortly after the Big Bang. Galactic history. Methuselah's trajectory through the halo offers clues about the formation and evolution of the Milky Way. Stellar physics. Understanding how such a star has persisted for so long helps refine models of stellar lifetimes, fusion rates, and energy transport mechanisms. Essentially, Methuselah acts as a cosmic laboratory, enabling astronomers to test theories about conditions that existed nearly 14 billion years ago. 6. The rarity magnifies its value. Finding a living fossil star is akin to discovering a well-preserved dinosaur skeleton in an area where fossils are extremely scarce. Because Methuselah is so rare, each observation provides disproportionate scientific insight, making it a cornerstone for understanding the first billion years of cosmic history. Unlike younger stars, whose properties reflect a universe already enriched by generations of supernovae, Methuselah allows astronomers to peek directly into the nascent universe, unfiltered by later stellar evolution. 7. Philosophical perspective. Beyond its scientific importance, Methuselah's status as a living fossil invites reflection. It has witnessed nearly the entire history of the cosmos, from the formation of the first galaxies to the emergence of planetary systems like our own. Observing it connects humanity to the deepest scales of time, offering a tangible sense of cosmic continuity. Just as fossils remind us of the fleeting span of individual species compared to Earth's history, Methuselah reminds us of the relative youth of the Sun, Earth, and humanity in the universe's grand timeline. Key takeaways. Methuselah is a living fossil of the cosmos, preserved almost perfectly since the universe's earliest epochs. Its extreme age, low metallicity, and halo location make it an invaluable record of early stellar and galactic evolution. Studying it allows astronomers to reconstruct conditions shortly after the Big Bang, providing insights unavailable from younger stars. Its rarity and preservation underscore the preciousness of ancient stars as keys to unlocking the universe's earliest secrets. In short, Methuselah is more than a star. It is a witness to the dawn of time, a survivor that carries the story of the cosmos in its light. Ongoing research into Methuselah and stars like it is a frontier of modern astrophysics, promising to reveal new insights into the early universe that were previously inaccessible. Even though Methuselah has been observed for decades, technology and methodologies continue to evolve, allowing astronomers to refine our understanding of its age, composition, and history. Future telescopes, particularly the James Webb Space Telescope, JWST, are poised to revolutionize the study of this living fossil of the cosmos. 1. The role of modern telescopes. Observing Methuselah requires precise measurements of light and spectra, as its extreme age and low metallicity make subtle features of the star critically important. Modern telescopes, such as Hubble, Gaia, and JWST, provide unprecedented tools. 1. Hubble Space Telescope. A Hubble has measured Methuselah's parallax with high accuracy, improving distance estimates and, by extension, age calculations. It has also provided high-resolution spectroscopy, allowing astronomers to determine chemical abundances, critical for understanding its metallicity and early universe origins. 2. Gaia Space Observatory. Gaia's mission is mapping stellar positions, motions, and distances across the galaxy with exquisite precision. By measuring the proper motion of stars like Methuselah, Gaia helps trace their orbits, offering clues about the Milky Way's halo structure and the star's journey through cosmic time. 3. James Webb Space Telescope, JWST. A JWST, with its infrared sensitivity, is capable of observing stars even in dusty or obscured regions. For Methuselah, JWST could provide unprecedented spectral data, revealing minute chemical fingerprints and providing deeper insights into the star's formation history and internal structure. 2. How JWST could transform our understanding. JWST opens new doors for studying ancient stars like Methuselah in ways Hubble cannot. 1. Infrared observations of low-mass stars. A Methuselah is a low-mass, metal-poor star, meaning its light is relatively faint and cooler in temperature. JWST's infrared instruments allow it to detect and analyze the faint light of such stars more efficiently than optical telescopes. 2. Detailed spectroscopy for metallicity. A JWST can perform high-resolution infrared spectroscopy, detecting even trace amounts of heavy elements in Methuselah. This allows astronomers to pin down its chemical composition more accurately, refining models of how the earliest stars synthesized elements and how the interstellar medium evolved. 3. Searching for companion stars or remnants. A JWST could identify binary companions or past merger signatures, revealing whether Methuselah has had interactions with other stars that might have affected its age or structure. 4. Benchmarking stellar evolution models. By providing highly accurate data, JWST will help validate and refine stellar evolution models for metal-poor stars. This has broad implications, as these models are also applied to other ancient stars across the galaxy and even in distant galaxies observed in the early universe. 3. Complementary observations and ground-based research. While JWST will be a game-changer, ongoing ground-based research also plays a vital role. 1. Large telescopes and spectrographs. Instruments like the Very Large Telescope, VLT, in Chile provide high-resolution spectra, complementing JWST's infrared capabilities. These observations help verify abundances of lithium, oxygen, carbon, and other key elements that are crucial for age dating. 2. Stellar population surveys. Surveys like SDSS, Sloan Digital Sky Survey, and future programs aim to find additional Methuselah-like stars, expanding the sample size. A larger population of ancient stars provides statistical context, helping astronomers understand how typical or unusual Methuselah truly is. 3. Astroseismology. By studying stellar vibrations, researchers can probe the interior structure of stars. Although Methuselah's faintness makes this challenging, advances in precision photometry could eventually allow indirect measurements of its internal fusion processes, offering further age constraints. 4. Why ongoing research matters. Studying Methuselah with new telescopes has profound implications. 1. Refining cosmic chronology. Better age estimates for Methuselah help calibrate the timeline of the early universe, providing independent checks against the 13.8 billion-year estimate of the universe's age. 2. Testing cosmological models. Observing extremely metal-poor stars informs models of galaxy formation, early star formation, and chemical evolution, bridging the gap between theory and observation. 3. Connecting to first stars, population 3. While population 3 stars have not been directly observed, Methuselah might carry their chemical fingerprints. JWST could detect signatures of elements produced by these first-generation stars, illuminating the universe's earliest epochs. 4. Galactic archaeology. By tracing Methuselah's orbit and chemistry, astronomers perform galactic archaeology, reconstructing the Milky Way's assembly history from its halo stars. 5. Anticipated discoveries and impacts. A chemical fingerprints of early nucleosynthesis, JWST, may detect tiny abundances of elements like lithium or beryllium, offering a direct test of Big Bang nucleosynthesis models. Improved parallax measurements. Although Gaia has already refined distances, combined JWST observations could reduce uncertainties even further, narrowing the margin of error in age estimates. A potential discovery of unseen ancient companions. JWST might reveal previously undetectable low-mass companions, providing insights into Methuselah's formation environment. A better understanding of metal-poor star lifetimes. Accurate observations of Methuselah allow astronomers to validate stellar evolution models for stars formed in a nearly pristine environment. 6. The long-term vision. Methuselah is not just a subject of curiosity, it is a gateway to understanding the first few 100 million years of cosmic history. As research progresses, each new telescope and survey will refine its properties, age, composition, and motion. Future observations will allow scientists to connect Methuselah to the broader context of the universe's evolution, from the Big Bang to galaxy formation. Methuselah will continue to serve as a benchmark for the oldest stars in the Milky Way, guiding our understanding of cosmic history for decades to come. Key takeaways. Our ongoing research is gradually peeling back the layers of Methuselah's history. JWST and other modern telescopes will provide unprecedented data on its chemical composition, internal structure, and motion. Studying Methuselah helps refine stellar evolution models, cosmic age estimates, and early universe chemistry. This research underscores the importance of ancient stars as living laboratories, connecting us to the dawn of time. Methuselah is not just an ancient star, it is a beacon guiding astronomers through the uncharted eras of the early universe, and future observations promise to uncover secrets it has kept for nearly 14 billion years. As we draw our gaze back to Methuselah, it's almost impossible not to feel a sense of awe. This star has been shining for over 14 billion years, predating even the formation of our solar system, our galaxy as we know it, and, in many ways, almost everything we take for granted about the universe. Imagine the cosmic epochs it has silently witnessed, from the cooling of the primordial universe after the Big Bang, to the formation of the first stars and galaxies, to the slow assembly of the Milky Way, all the way to the eventual rise of life on a small blue planet we call Earth. Methuselah is a living relic of cosmic history, a direct connection to the universe's earliest moments, and a beacon of continuity across incomprehensible spans of time. Every photon of light that reaches us from Methuselah has traveled centuries of light years, carrying with it the imprint of the star's ancient past. Each flicker, each subtle pulse of radiation, is a whisper from the dawn of time, a message that transcends generations of stars and civilizations. In a very real sense, looking at Methuselah is like looking back in time to a universe that existed before our Sun, before our Earth, before humans even walked the planet. Its endurance reminds us that the cosmos operates on scales far beyond human lifespans, that time itself is a river that flows across eons, and that the stars are the storytellers of that immense chronology. Methuselah has not only witnessed cosmic events but has also played a role in shaping the universe. As one of the earliest stars, its nuclear fusion forged elements that would later seed the cosmos, contributing, however subtly, to the chemical foundations that would eventually give rise to planets, life, and us. It's humbling to realize that the atoms in our bodies were forged in stars much younger than Methuselah, but the processes it represents set the stage for everything that followed. In a way, Methuselah is both ancestor and witness, a cosmic monument to the universe's enduring march forward. Reflecting on Methuselah's journey also highlights the fragility and rarity of such ancient stars. While the universe is vast, stars this old are exceptional, surviving for billions of years against cosmic odds. They are nature's time capsules, containing within them the signatures of primordial processes and the remnants of the very first stellar generations. Their persistence challenges us to rethink the nature of time, survival, and change on cosmic scales. Every new observation, every improved measurement, allows us to decipher the messages embedded in their light, offering glimpses of an era we cannot otherwise experience. Methuselah invites us to adopt a longer perspective, reminding us that our human timeline is a mere heartbeat compared to the ages over which stars and galaxies evolve. It encourages a sense of humility and wonder. Humility before the vastness of time, and wonder at the intricate tapestry of forces, processes, and phenomena that have allowed this star to burn steadily for nearly the entire history of the cosmos. Through Methuselah, we gain not only knowledge of cosmic chronology but also a profound emotional connection to the universe's narrative. A narrative that stretches far beyond Earth and human history, yet somehow touches both. In the grand story of the universe, Methuselah stands as a monument to endurance and cosmic memory. Its existence bridges the primordial past to the present, linking the unfathomable birth of the universe to the human endeavor of understanding it. As we study this star, we do more than measure age or chemical composition. We participate in a dialogue with time itself, listening to the echoes of the universe's formative years. Methuselah reminds us that the cosmos is not static, not fleeting, but a dynamic continuum in which each star, each galaxy, and each event contributes to a story billions of years in the making. Now, let's leave the viewers with a question that sparks both imagination and introspection. If a star could remember everything it's seen, what stories would Methuselah tell? Consider it for a moment. Methuselah has witnessed nearly the entire history of the universe. It has seen galaxies form and collide, stars ignite and die, and cosmic structures evolve over billions of years. Its very existence is a chronicle of cosmic events, yet it remains silent, communicating only through the faint light that reaches us across the vast void of space. What secrets are encoded in those photons? Could they reveal the violent births of the first stars, the slow accretion of matter that built the Milky Way, or even the intricate chemical evolution that eventually enabled planets like Earth to exist? This question is more than poetic. It touches on the fundamental human desire to understand our origins. By studying Methuselah, astronomers are, in a sense, listening to the stories of the universe's earliest epochs. Each spectral line, each precise measurement of distance and luminosity, is like uncovering a sentence in an ancient manuscript written in light. And yet, despite all our technological prowess, there is still much we cannot decipher. The star's memories are partly accessible, but much remains a mystery, reminding us of both the immensity of cosmic time and the limits of human knowledge. Inviting the audience to imagine Methuselah as a storyteller bridges science with wonder. It encourages viewers to think beyond numbers and measurements, to visualize the unfolding of cosmic history as an epic narrative in which our Sun, our Earth, and humanity are only the latest chapters. It also emphasizes how tiny and fleeting our own story is when compared to the life of a star that has burned steadily for 14 billion years. By framing the scientific discussion this way, we leave the audience with a sense of connection to the cosmos, as well as curiosity. What did the early universe look like? How did the first stars shape the galaxies we see today? And if stars like Methuselah could somehow communicate their experiences, what lessons might they impart about endurance, transformation, and the passage of time itself? Ultimately, this question encapsulates the core wonder of studying ancient stars. Methuselah is not just a collection of atoms and energy, it is a living relic of the cosmos, a silent witness to the unfolding drama of the universe. It challenges us to think on timescales that dwarf human history, inspiring both awe and a deeper appreciation for the vast, interconnected story of existence. So, to every viewer watching, as you gaze at the night sky, ask yourself, if a star could remember everything it's seen, what stories would Methuselah tell? Perhaps, in listening carefully through the tools of modern astronomy, we are beginning to hear the faintest echoes of that cosmic memory, and in doing so, gaining insight into the universe and our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.